A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. So, hello, a very warm good morning to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session of geography, where today again we shall be pursuing on from where we left off the discussion on Saturday. That is, where we had the discussion about the different stages of river movement, the different types of landforms created by the action of the movement of the river, the different types of landform created by the action of the glaciers. What do we understand by karst topography? And also the chemical erosion of the rocks as is carried out by the water that creates sinkholes and cave sections underground. And we have seen the examples in various parts of India also as it lies. So that is what we had covered on the portion or in the session for Saturday. And today we shall be moving ahead with the same concept, with the same logic about the carrying capacity and the erosional ability of any agent of nature, how it is related with the speed of that agent of nature. With that same logic, we shall be looking at the landforms developed by waves, wind, as well as by the sea waves. Now, starting with the aspect of the landforms developed by wind. So, when we talk about the landforms developed by wind, you have to understand that wind is also able to erode certain materials from any area based purely upon its speed. So, wherever the wind speed is going to be very high, it is going to be able to erode very easily. And if the wind speed is particularly lower, that is where the deposits they start to happen. So this is to be observed in those areas where the wind speed is very high. And which are the areas where the wind speed is very high? When we talk about, let's suppose, the desert areas, the arid and the semi-arid regions. So those are the regions where this wind speed will be very high because there won't be many obstructions in the pathway of the wind, which can reduce the speed of the wind thereby. So that is why these landforms are experienced in areas arid and semi-arid areas, regions where the wind speed is very high. Okay. So when the wind speed is very high, that ends up creating that force which can erode particular kind of rocks, which can carry certain materials over a particular distance. Now, as wind also comes into motion, you will find that you have certain basic phenomena that you will observe. For example, let's suppose you consider or you talk about into consideration a desert land, a desert area. Now, here, as the wind moves, as the wind blows, obviously it will have certain velocity, it will have a larger velocity because we are talking about desertified areas where not much of the obstruction is offered in the path of the wind. Now, here, the wind will be able to uplift and erode various different types of particles. Now, let's suppose you have a sandy area or a sandy desert region. And there the wind is moving with a considerable amount of speed. Now, the wind will be able to lift that amount of sandy particles which are present on the ground surface. But then, will all the particles be of the same size? Obviously not. Certain particles will be larger in size, certain particles will be smaller in size. So, as the wind comes in, while the lighter particles, because they are lighter, the lighter particles will be uplifted by the wind for a certain height. Whereas when we talk about the heavier particles carried by the winds, they blow very close to the level of the ground surface. Okay. So, wind carries lighter particles aloft, while heavier particles are carried closer to the ground surface. Closer to the ground surface. Now, due to this process or the property of the wind, they are also able to create various different erosional as well as depositional structures. And as is the case, almost all of these erosional and depositional structures are to be found in the desertified areas itself. That is where you'll find them to be restricted into. So here, amongst the erosional structures, if you analyze, one of the very important or the very commonly found erosional structure in the desertified areas is going to be the mushroom tables or the mushroom rocks. The mushroom table structure or the mushroom rock structure. Okay. The mushroom rocks. Now, what are these mushroom rocks? So the name is ascribed based upon the shape that they have. We do know the shape that the shape that they have. Generally, what is the shape that the mushrooms will give you? This will be the shape where they are wider on top and basically thinner at bottom. Something very similar will be observed in case of the rock surfaces as well, in case of the rocky portions and the rocky outcrops that you find in the desertified areas. And these are formed based on the same property, that as the wind blows, it will carry the larger particles closer to the ground surface, and the smaller particles will be carried aloft. So here, imagine if you have a larger rock structure. Imagine if you have a very large rock structure like this. Now here, as the wind blows, with the same logic that the larger particles are moving closer to the surface, finer particles are moving higher up. So here you will have these finer particles which will be rubbing against the rocky portion. So it will end up providing a kind of a polish to the rocks, just like when you rub any surface with sandpaper, you end up smoothing the surface, isn't it? So in a very similar manner, by a method of abrasion, by a mode of abrasion, the finer particles, they end up polishing the top surface of the rock here. Okay, so the finer particles polish the upper portion of the rock. Whereas when we talk about the base of the rock, now the base of the rock is consistently being attacked by the larger particles. The larger particles which are sticking closer to the ground surface, they will be consistently hammering and chipping at the base of these large rocks. So as a consequence of that, the base of these hard rocks, they are continuously shaved off. Okay, continuously as the wind moves in the same area and the wind carries these larger particles, drags these larger particles. So think about it, that closer to the ground surface there will be a consistent hammering action which will be observed for the larger particles which are present. So that is where they will end up shaving off the portion of the rock closer to the ground surface. So larger particles chip away the portion of the rock closer to ground surface. So as a consequence, you have the landform. What is the kind of landform which develops? So for here, for example, eventually you will find that closer to the base, the rock has been eroded. And this process further continues. The wind action will further continue. Observe here, the wind will be attacking the base with the larger particles, and the wind will actually be moving across at a slightly greater height, and it will be the lower or the smaller particles which will provide that polish. So as these larger particles they continue to hit, furthermore it will lead to a further formation of a mushroom like structure. Eventually what will happen? As this continues, the base will grow on thinner and thinner. And you have a formation of a structure somewhat like this, which is also known as a mushroom table because it is flattish at the top and has got a mushroom base at the bottom. That is why sometimes also referred to as the mushroom table. Now here, as this process continues, eventually you come across a situation where the rock will break from the base itself. And there, the rock, once it is broken at the base, then maybe the top portion will fall off. The top portion will fall off somewhere here, right? Now, then again, there will be further action and creation of a mushroom table on this rock also. So, like that, multiple such reiterations and formations of mushroom table are observed in the process where the larger rock systems in the deserts they are converted and pulverized into many smaller rock subpieces. So that is the formation of your mushroom table. And then you have the formation of yardangs. Now, what are yardangs? Now, yardangs are very unique and specific desert landforms that you observe, which are erosional structures and eroded structures, where not only the top surface of sand and soil is eroded by the wind, but after the topsoil is eroded, it is the base rock, the parent rock, which gets exposed. And that parent rock is also then eroded by the action of the wind. Okay, so in this process here, you will observe that process of erosion carries away the sand and the topsoil, exposing the base rocks. Okay, the base rocks are exposed, right? And then these base rocks are further eroded by the action of the wind. Okay, so here again the same principle, guys, what we have been observing since the time of the river movement and the action of erosion carried out by the river, the same principle will be observed here also, where as the wind speed is high, it will have a lot of power with it to carry different materials. So it will end up eroding away and chipping away various different materials. So what you have as a situation is, for example, if you consider any particular area, right? Now, this might be covered with sand and topsoil on top of it. And at the base, you might have the presence of various different rock structures, right? Unweathered rock structures, as is the case with the formation of a soil. Generally, the soil formation and the sand in any area you will find is basically a weathered particle of the base rock. It is the base rock which would have broken into many small fragments to create that soil and eventually that sand also. So the wind erosion, it will erode the top layer of the soil. It will carry the top layer of the soil and the sand away. And eventually it will lead to a situation where the base rock is then exposed. In various different pockets, the base rock gets exposed. Okay. Now, this exposed base rock then is subjected to the wind movement and the wind pattern here also. Now, here you might have a query that why don't we observe a mushroom-like structure getting created here or a mushroom table getting created here? That is because of the structure of the rocks and also because of the continuity that the rocks have. And unlike the mushroom rocks, here these are not very large structures. These are oftentimes not very large structures. Sometimes they get created as large areas, but not very large structures. And eventually these will also get eroded as per the direction of the wind. So eventually these will also form a kind of a streamlined pattern in the direction of the wind. Okay. So in this case, initially, in the process, first of all, the sand or the topsoil, that is to be removed, that is to be eroded. And once that has been removed and eroded away, it is the base rocks which are then attacked and the base rocks which are then eroded to form a streamlined ridge-like pattern in certain cases. And that is what we refer to as yardangs. Yardangs are not that greatly to be found in very high proportion in Thar Desert of Rajasthan. But when we talk about, let's suppose, the Sahara Desert of Africa, you'll find a lot of yardangs, particularly in the northern part of the Sahara Desert. Also, if you consider the desertified areas in the Arabian Peninsula, for example, if you consider Daste Lut in the region of Iran, if you consider Rub Khali, these deserts, Rub Khali, the region of Saudi Arabia. Now, all these particular deserts also you will find the presence of lot of these yardang-like structures. Now, here, after this, you come across another kind of erosional structure which is referred to as a deflation hollow. Now, deflation is exactly the opposite of inflation. So when we say inflation, means something has basically swelled up, something has risen up. When we talk about deflation, that means an existing area has basically gone down. So there has been a deflation which has been carried out. So when we talk about the desertified sand or the desert areas, now the sand particles, they are all not all uniform, right? If in general, if you have ever experienced the desert areas, you would have found that it is not the case that everywhere you will find the powdery sands only. In the top layer also, in some portions you will find slightly larger particles of sand and soil and parts of rock, etc., and then interspersed with the finer particles which are also present. So as the wind comes into motion and the stronger wind movement is observed, obviously, the larger particles of the sand and soil won't be carried by the wind because they are heavier. But the finer particles, the wind can very easily carry them away. So when you have, let's suppose, the wind motion, right? So the finer particles, because they are lighter, they will be carried away. Whereas the heavier particles, they shall be left behind. So as a consequence, you have a kind of a deflated structure which gets created. And that is what is regarded as deflation hollows. Okay, so where the finer particles are picked up and the larger particles of the ground surface are left behind. Now, all these eroded materials will be deposited by the wind also. When will the wind start depositing them? Wind will start depositing them when their speed reduces. That is when the carrying capacity of the wind will also reduce. That is when the wind will start depositing. So the wind basically deposits all these carried materials in the form of dune like structures, or sometimes even the finer particles carried away or shaved away by the wind. They are deposited in large plain like areas. So the plains created by the wind deposits, that is what we refer to as lowest plains. So here the lowest plains that you observe, these are your plains. Plains created by deposits, finer deposits carried by the wind. For example, when we talk about the western portion of China, the Xinjiang region of China, for example, in the Xinjiang region, I hope you would have heard about the Xinjiang region of China, very rich in critical minerals such as lithium, etc. So that is why that is also, by the way, one of those areas where China's entire iron fist policy of governance is something which is demonstrable. So western portion of China, which is restive, which is not very well grown, and which is not very productive agriculturally as well, because that is a drier area. So in that Xinjiang region of China, you will find the presence of these vast fertile lowest plains. So that is where these lowest plains come into existence. But in general, when the wind carries these materials, it will end up depositing these materials in dumps, in large chunks. And that is what we refer to as sand dunes. So when you hear about the sand dunes, these are simply the deposits made by the wind action. So as the wind here basically ends up moving with all the materials, it will dump them over. It will create these dunes like structure. Now, depending upon what is the direction of the wind, or in an area, if you have multiple different directions of winds which are experienced through the day and through different parts of the year, the shape of the sand dune, and also for that matter the position of the sand dune, keeps on shifting. It is, these dunes are not permanent structure because these are simply structures of sand. So as the wind movement continues, these sand dunes also keep on shifting. So dunes are prone to shifting due to the movement of the wind. Due to the movement of the wind, that is why these dunes. So for example, here if you observe this in particular image, you will observe that if the wind speed, or if the wind, let's suppose, is moving from different directions converging in an area, then you will observe that the sand gets piled up in a particular direction, in a particular pattern. The sand gets piled up, isn't it? Now, this piling up of sand also creates these dune-like structures, but these are longitudinal. So these dunes are longitudinal in nature. Then, for example, if the wind velocity is quite consistent and is in the same direction, then what do you observe? You will observe these parallel existence of these sand dunes, where these sand dunes are virtually parallel to each other, which are referred to as transverse dunes. Okay. Now, for example, if you look at the cross section of these transverse dunes, it will appear to look somewhat like this, where after one dune, again another dune is there. Before that, again another dune-like structure is there. So they are almost parallel to each other. Okay. Now, traditionally and historically, This has been utilized by merchants and traders alike, where they would utilize this idea and knowledge about the wind motion and the shape and the pattern of the dune also would give them an idea about in which direction the wind has been blowing in an area. So majority of the merchants and the traders, they would basically pursue this pathway. Majority of them would pursue this pathway, where basically at the shelter of the dunes, they would virtually move from one region to another. So that is what is a transverse dune. Now, sometimes the wind comes in and converges from all different directions. And when the wind converges from all directions, you have this dune which is piled up with its arms basically flailing and extending in all different directions. So that is what is referred to as a star dune. So in the case of a star dune, you have the winds coming in from all different directions. Okay? Then you have a unique kind of a dune formation, which is a crescent shaped dune formation, which is referred to as a barchan. Now, these barchans, they are also basically in their basic DNA, they can also be considered as a dune. But then, when we say these or when we talk about these barchans, so what they are? So these barchans are larger dunes where the central portion has simply slipped off. So you might have had a larger dune-like deposit, and in that larger dune-like deposit, due to the weight of the sand from the central portion might have slipped off. So that is where you have the slip face here. From this portion, whatever sand would be accumulated, that would have slipped off, creating these protruded arm-like structures. So observe this. Observe this structure. So I hope you are able to observe the extension carried out here, right? So this extension which is carried out on both sides. So that is what you accrue as a shape or the creation of a barchan. This you will find in large numbers even in Thar Desert in Rajasthan. Almost in every desertified area, you'll find the presence of these barchans. And these get created when the dunes, they become very large in size, where the weight imposed from top is very high. And that would have been your own experience also, if you recount how you would have recount or when you would have experienced a lot of mound of sand or a lot of heap of sand, and then if you put weight on top of that sand, what happens? The base simply slips away, doesn't it? Right? Sand is not that solid a structure. So when you impose a lot of weight on sand, the base simply gives way. So here also, in this kind of a dune, when a lot of weight is imposed, then the base of it, the bottom of it, simply gives way, and that leads to the creation and the formation of barchans in the process. Okay? And then the last set of landforms that we will talk about is the landforms developed by the wave action. So when we encounter waves, sea waves, now in that case, the coastal areas, they experience both action. One, the physical force offered by the waves. When the waves, they come and crash on the rocks nearby, right, at the coastal rocks. So the physical force offered is also very, very high. So due to that physical force in itself, let's suppose you have a rocky structure like this, and you have in this sea area, the waves, they come and they hit these rocks. So with that force of the waves itself, the rocks will start collapsing. The rocks will break into smaller portions. For example, if you ever happen to venture across the coastal areas on the west side, western part of India, that is the western coast, you will come across many of the features where very closer to the coastline you have the rocky structures, but the rocky structures have been eroded to varying degrees. If you ever happen to take a look at a longer stretch of the coastline, the generally the condition is that whenever we go to visit the coastline, what do we see? We basically search the or let's suppose you are going there with your family or your friends. You basically search, okay, what are the beaches available in this area, and maybe you visit those beaches. But in those beaches, you'll find generally a kind of a uniform structure. But when you venture across the coastline, when you explore the coastline, especially our western coastline, you will come across many of these erosional structures where the rocks have been eroded to varying degrees. You'll find in few areas the larger rock structures have been reduced into many smaller parts. For example, in Kerala coastline, the Malabar coast, you will come across the fact, and you can imagine just by taking a look at these rocks that at one point of time how massive these rocky structures would have been. You have certain areas where that process of erosion is being carried out, and over a period of time it will be much more significant. For example, the Konkan coastline across the region from Ratnagiri, Goa, all the way till Gokarna, in that entire area you will find that erosion is being carried out, right? So here, not only does the physical impact of the sea waves create a kind of a breakage of the rocks, but also you have to understand that sea waves or the sea water is salty in nature. And being salty in nature, it can also instigate certain chemical reactions or chemical process of dissolution of these rocks. So thereby they can also end up weakening the rock structure. So in the landform created by the wave action, you have both the forces or both the processes acting simultaneously. One is the physical, sheer physical impact offered by the sea waves, and second is the chemical process of dissolution which is carried out by the salty sea water. So as these waves they end up moving continuously, they end up shaving off the rocky portions in the coastline. Many of these rocky portions, when they get broken down, they will get deposited immediately in that region itself. And that is how you have the formation of the various different types of beaches. That is why once you visit different types of beaches, you will come across a realization, or you will come across the fact that not all the beaches have the same type of sand, not the same coloration of the sand also. For example, certain areas in Andaman Nicobar, in Lakshadweep, in Maldives, in many portions of the globe, you will find that in the beaches, the sand is whitish, right? You have white sand. Whereas when you consider other areas across the eastern coastline, you will find a reddish or a kind of a yellowish sand pattern. Similar is the case across the western coast also, right? So that also is basically created by the breaking of the rocks. The rocks would have broken down, would have been broken down by the action of the sea waves, and the smaller particles of those rocks would have formed those beaches. They would have been further broken down, and like that you have these very fine sandy beaches. Older a particular sandy beach is, finer the sand particles would be. If a sea beach has been created very recently, you'll generally find larger sand particles to be ingrained in that particular portion. So that is a common feature that you will find. Now here, when you take a look at the erosional structures, you have cliffs, terraces, etc., all caves, then stacks, stumps, all of them, they get created. Now in this case, let us first of all observe the cliffs. Cliffs are what? Cliffs are something that you even find across the land areas. Cliffs are regions where you have almost a vertical wall like descent, right? So, this is going to be a cliff. So, or rather, this is going to be a cliff, right? So, how is it that coastal cliffs are created? Now, these are very unique features, by the way. These are not to be found in every part of the globe. Very rare areas across the globe will you find the presence of such magnificent sea cliffs. In India, you find them to be present in a region in Kerala, where again, that region is very popular, particularly with foreign tourists, because when people are aware about how rare that is, so generally you will have foreigners flocking that area. Once the foreigners they start flocking that area, that is the sad reality, even though we agree it or not. When the foreigners they start visiting an area in large numbers, then we Indians also realize that okay, there must be something special in that area, and then we Indians also start visiting them. But having said that, Varkala in Kerala, I hope you would have heard about that name. If you have not visited, you should. Absolutely a very beautiful place. So, Varkala in Kerala has got that presence of sea cliffs. Okay, that is something that you will observe, that you will notice here. Now, how do they get created? So, just observe the size of it, the magnitude of it. Observe this height. These are the beaches, right? Almost negligibly visible. These are your small structures thereby. So, how do they get created? So, it gets created over a continuous repeated process of erosion. So, at one point of time, the rocks in this area would have been somewhat like this. Let's suppose the rocks in an area would have been somewhat like this, with this as the sea water. Okay. Now, as the sea waves would hammer the bottom directly and would attack the bottom directly, the bottom portion would get eroded, right? There is a simple mechanism to it, that the physical force of the sea waves would be so very high that they would attack the bottom. So, in the bottom, you have a creation of a structure which is somewhat like this. Now, here at the bottom, you observe this structure. But then the sea action would further continue, isn't it? It is not as if the sea waves will relax, that okay, now we have created a mark. Now everybody will know that sea action has taken place here. Now let's go back. That won't happen. So what will happen in this case? This process will further continue. This process further continues. So you have a creation of a structure somewhat like this, with a rock which is overhanging. Now, this overhanging rock, this is also what is referred to as a notch. Now, if I ask you to apply your logic and then tell me, this notch-like structure, will it be stable in its existence, or will it be unstable and liable to fall? What do you think? Will this notch structure be stable, or will it be unstable? What does your logic tell you? Very good, beautiful. It will tend to collapse. It will fall, right? Because it is overhanging. It will be exposed to the actions of rainwater and also the sea spray and also heating, cooling. So weathering action will also be instigated, and also it won't be, it is an overhanging structure, so it won't be stable. So this notch falls away. So when this notch falls, what is the kind of a landform that you will have? You will have a landform somewhat like this, right? A structure somewhat like this, isn't it? Now, again, the same process will be continued by the sea wave action, where the sea waves will attack the bottom. So, again, you will have a creation of a structure somewhat like this. Again, creation and formation of a notch. That notch will also collapse. So like that, you will have the formation and creation of these cliff-like structures. Generally, the cliff-like structures, and for the cliff-like structures to be created, you need to have those kind of rocks in the coastal area which are soluble in water, which water can dissolve up till varying degrees, not completely, but up till varying degrees. So in regions where across the coastline you will find sedimentary rock formation, including the rocks such as limestone, you will find a lot of this kind of a formation taking place, or the sea cliff formation taking place. So sea cliffs are consistently to be found in areas where The coastal rocks are sedimentary in nature because easier to erode. Okay. So, for example, in the region of Scottish Highlands, right, in the Western Europe, in the region of Scottish Highlands, and in some portions of England also, you'll find a lot of these sea cliffs getting created by the process of erosion. So, in many of those areas, you'll find limestone as a rock feature, which is very prominent. Right. In Varkala also, you have sedimentary rock formations, the sediments that you will find, the red sedimentary rocks that you will find to be present in the region around Varkala, where you have the formation of these sea cliffs. So that is a common phenomena and a fundamental which is observed. Then we come across spits and tombolos. Now, spits and tombolos, they are depositional structures. These are basically your depositional structures. Depositional features. Now, how are these depositional features created and where they are created? So, generally, when the sea waves come over, they will try to carry out their own deposits also. So, let's suppose we consider a land area. Let's suppose we consider a land area, right? Now, obviously, the coastal land is not going to be absolutely straight or flat. Let's suppose we have a land area and a coastline somewhat like this. Let's assume that this is the region of the sea. Now, as the sea waves come and are taken back, they will carry out their own deposits, right? These sea waves, they will carry out the deposits of the finer particles that they have brought over. Now, in certain cases, in certain instances, you'll find that, let's suppose the sea waves, they try to deposit something here. They will deposit it in this region, in this area, they will deposit it, right? Now, across the coastal area, you also have the presence of a wind which blows parallel to the coastline almost. You also have a wind motion parallel to the coastline, which is also known as a longshore wind motion parallel to coastline. Now, in that case, if the sea waves, they want to create a kind of a deposit, that depositional structure will be shaped by the wind pattern also, isn't it? So immediately observe if the sea waves, they start depositing here. Now, the shape of the rest of the deposits will be shaped by the direction of the wind. So it will be deposited in the direction similar to that of a wind, right? So which will be attached obviously to the mainland. So this deposition that you observe, these deposits parallel to the coastline, influenced by direction of the wind, These are your spits. These can be oftentimes many kilometers long. If you look at the image of a spit, this is what a spit appears to look like. Observe this. This is what a spit deposition and creation of a spit, this is what it looks like. So here, this is your coastline. I hope you will be able to figure that out in the image also. This is your coastline. And here, this is the deposit which is attached to the coastline. But observe the shape of this. The shape, it has been almost shaped as per the wind movement and as per the direction of the wind. Otherwise, why would a deposit have this kind of a shape associated? So these are your examples of spits. Okay. Sometimes when we talk about these sea waves, for example, in the region around Kerala coastline, that is where you would have observed it if you belong from that area, or if you have visited Kerala, the God's own country, you would have experienced this. That sometimes, owing to the shape of the coastline or the bottom relief feature of the coastline, where the bottom relief is not very deeper, for example, in those areas, oftentimes these sea waves, when they carry out their deposits, they deposit materials which are parallel to the coastline. Right? You will come across sandy features which are not attached to the coastline, by the way. The sandy features which will get deposited almost parallel to the coastline. Obviously, in this area, basically, if you have to analyze the cross-sectional view of it, just I'm giving you a point of inference here. You don't necessarily have to jump into that much detail. But let's suppose this is the coastal area or the coastal land area. This is where the water body is in existence, the sea water is in existence. So you might come across a deposit which is not attached to the coastline, but it exists parallel to the coastline. Obviously, in shallower areas of the water body, you can have creation of these deposits. Now, this will have some water on other side also. These are what are known as sand bars. These are known as bars. Okay, so these get deposited in areas where, due to the topography of the landmass, the sea waves, they are not as strong. The sea waves basically are a bit moderated in terms of their impact. That is where you will experience them. Now, when you would have visited the coastal areas, you would sometimes have also come across a nearby small island of sorts, right? Not always all the islands are situated very far away. You have few of the smaller land masses which sometimes are very close to the coastline. Let's suppose you have a small island like structure which is very close to the coastline. Now, if ever you would have taken attention and observed that how the sea waves behave, or the motion of water does exist in the region around, you'll find that the sea waves will attack this island with the strongest of the force. But in this region, in the rear end, the speed of the water will be very, very low, because obviously the water would have been diverted and then would be coming back. So that is where here you'll find that the deposits, they will be very significant. In this region, the deposits would be significant. And these deposits can end up joining any of these small island-like features to the coastal mainland, right? A structure that you see somewhat like this, where the deposit has been linked to the mainland. And that deposit which links one particular island to the mainland, this is what is also referred to as a tombolo. Okay, and this island is then referred to as a tide island, which has been tied with the mainland. Tide island. Okay, which has been now joined with the mainland. So a tombolo is like a deposit which is created. This is your tombolo. So these tombolos, they get created as you have these small islets, they get joined to the mainland, because here the sea wave action might be very strong here. But when it comes to here, the movement of water is very, very slow. So as the movement of water, wherever they will be slow, there will be observed these deposits. These deposits have been carried out in this region, And over a period of time, these deposits have become continuous and they have joined this island to the mainland, forming these tide islands. Then overall, if you take an overall overview of it, here you will observe, for example, the when you come across, especially in the southern coastline of Europe, that is the Italian coastline in particular, where you will find a lot of these rocky structures very close to the coastal area. Now, in many of these rocks, depending upon their chemical properties, you will find that the seawater is able to erode both by the chemical erosion as well as physical erosion, and can end up creating massive cave like structures in the coastal areas also. But mind you, despite how massive these cave-like structures might appear to be, they are nowhere in comparison to the limestone caves that we studied in the karst topography. That cave portion will be much more extensive because the rocks, the limestone themselves, they will keep on dissolving wherever the water reaches. Here, it is the chemical property of these rocks, as long as they will allow the water to erode that structure. Having said that, in certain areas where you have the lime coastline consisting of the limestone, there again the cave structures can end up becoming very, very deep in nature. But these caves then will have the penetration of water, where the water goes in continuously. Sometimes the water will be able to penetrate from the other side also, or come out from the other side also. So in that case, it is no longer a cave anymore. It becomes like a tunnel like structure. Over a period of time, it gets converted into this kind of a structure, right? Where the water can move from one region to another underneath, and you have an overarching platform on top, right? An overarching or an overhanging platform on top. Now, this is what is known as an arch. Okay, this is what is an arch. Now, again, apply your logic. The roof of arch, will that be basically having a kind of a stable feature? Obviously not. This roof of arch will also be very unstable. So as a consequence of that, that roof will collapse eventually. And once that roof collapses, you are left behind by this platform like structure, right? Which are known as stacks. Now, this stack will also experience weathering and erosion to varying degrees. And that is where you will come across the formation of small stumps. Okay, so stacks, when they get weathered and eroded, they will be reduced to stumps. Okay, so these are the features that you find generally associated with the coastal landforms, and that will be the entire portion of this landforms, right? We have already discussed the prelims and the mains type of questions associated. We have already discussed the type of answers that you need to be writing for all these different types of questions, the type of questions to be expected from these portions of landforms also that we have discussed. So just revise those, and that will be the end of geomorphology. Okay, now after this we come to the portion of climatology, and we initiate the discussion for climatology. Now, climatology basically is the study of the climate around us. Now, the climate around us basically is the factor which ends up determining not only the kind of life that we live, also ends up determining that the food that we consume, the region where we choose to live, the clothes that we wear, and eventually the crops that we grow, the type of animals that we have, everything, the type of plants that are in existence, everything is a sum product of the climate. So once we know the climate of a region, we get an idea about many other perspectives of life in that area also. So that is why climatology becomes an important determining factor in geography. And climatology, in this journey, we are going to initiate the discussion from the very basics of what do we understand by insulation, temperature, what is atmosphere, the various layers of atmosphere. We'll start from those basics, the formation of atmosphere, and then slowly and steadily we'll move on. We shall push on. We shall be talking about the areas, for example, about temperature inversion, lapse rate, all those factors we shall be talking about. Eventually, we shall be moving into the wind motion, the planetary winds which are in existence across the various different parts of the planet, the pressure belts, the pressure zones which are in existence, then the local wind systems. What are local wind systems? Why is it that rainfall occurs? How is it that the cloud formation is observed? How is it that, or why is it that lightning, thunder, and lightning is observed? What are the different types of cloud? Why is it that fog gets created? Why is it that cyclones occur? What are jet streams? What do we understand by El Nino, La Nina? What do we understand by Indian Ocean dipole? All these factors we shall be studying in the portion of climatology that shall help us eventually understand Indian climate and Indian monsoon. Once we have understood that, then we'll take an overview of the world climate also, right? In geomorphology also, we have been taking a look at the geomorphological features present across the world. Similarly, in this portion also, we shall be talking about the different climatic features which are prevalent in different parts of the world and why is it so. For example, why is it that the region of Mediterranean experiences rainfall only in winter, not in summer? Why is it that the region of Britain experiences rainfall throughout the year? Right. So these factors, and also how do they end up impacting the type of vegetation that you see in that area? All those factors we are going to discuss in climatology. Having said that, these portions of climatology, they are very conceptual in nature. One particular concept will lead you to the other particular concept. Okay. And it is as simple as it can be that if you miss out one of the basic concepts, you will have a really tough time understanding. For example, as is the tendency, that let's suppose you miss out this particular module and you think about it, that why will I study atmosphere and temperature? I know what is atmosphere, I breathe in every day. I know what is temperature. Today is 21 degrees Celsius. Why to attend atmosphere and temperature? I will come when they will talk about tropical cyclones, because that is what I heard in news and that is what sounded interesting to me. So if that is the approach, trust me, write it somewhere. You will never be able to comprehend what complex phenomena such as jet streams, cyclones, El Nino, La Nina, what they are, if you're not sure about the basics. And generally, what I have found out as my experience over the past few years, I have seen this tendency amongst the candidates also, that regardless of the caveat that I attach in the initial portions of climatology, they do take it how the candidates will study everything. They do study it in a similar way. And after 5 to 7 classes of climatology, suddenly people will come that I'm not able to understand something, or I'm not able to make sense of anything in climatology. So, there, understand, any individual who is unable to understand climatology is because this module has not been understood. So, this module and the immediately next module, these two modules, if you internalize within yourself, if you understand the basic logic of it, then you will not face any difficulty in understanding and analyzing even the most complicated of the climatic phenomena across the world. Okay, so even your understanding of Indian monsoon, jet streams, Maran-Julian oscillation, all of that becomes a cakewalk if you have a good clue about these modules. So this is also a reminder for you guys that it might be possible 1 month down the line, 15 days down the line, 2 months down the line, 3 months, maybe you are appearing for the exam in 2025, 2026. It might come across a situation, or you might come across a situation where climatology is a bit dicey, it is a bit shaky, where certain concepts they do scare you. So don't worry at all. Immediately jump to these basic modules, read it slide by slide, and try to understand what these talks about, how temperature is experienced, what are the factors which vary the temperature. Analyze these, and eventually rest of the climatology will be addressed. Okay, now this is important and relevant both for your prelims as well as for the mains examination. So when we talk about the prelims, so from this portion questions have been asked. Basics, of heating and cooling. Okay. Then layers of atmosphere and properties of these layers. Then after that, you also have questions which have been asked previously from the portion of lapse rate, isotherms, and also temperature inversion. Okay, these are few of the common things that you will find that UPSC has been asking. Factors on which the temperature will vary in from one region, the different amount of heating as experienced over the land areas as compared to the water body. So the variation in heating between the summer and the winter season, for example. For example, if I ask you, during the winters, which is going to be colder, the oceans or the land areas? What do you think? During the winter months, which is going to be colder? What does the logic tell you? Very good. So here, as you can see, majority of you have written oceans. Quite some number of you have talked about the land areas. Few of you have talked about the lands also, but majority of you, your logic tells you that during the winter, ocean will be colder. But that is not the case. Why that is not the case? That is something that we are going to analyze in this. Then, from the mains portion or in the mains examination also, this area has been frequently visited and revisited. So here, layers of atmosphere, okay, urban heat island, and albedo. Then after this, factors influencing temperature, insolation and temperature. Then temperature variation, inversion. Okay. So these are the factors or these are the areas that UPSC will ask you, will tend to always frame a question in the mains examination from this area also. Understand that this is one of those portions where UPSC has got a scope because there are so many unknowns out there in climate. There are so many different factors out there in climate, the aspect of climatology, that UPSC has got a scope to twist the questions ever so slightly, and then to ask you those twisted realities and those twisted concepts which oftentimes confuses the candidates. And to be very frank and fair, if you observe the prelims paper previously also, if the questions are asked from geomorphology, they are very straightforward, right? So none of the good candidates will miss out on questions of geomorphology. I'm talking about good candidates. I'm not talking about the candidates who are out there to fill up the number of participations, right? You have many of those candidates also amongst you also who will generally carry out this process of that I'm preparing for civil services as if they are doing a national duty out there. and every day I'm studying 3 hours. What more do you want from my life? I want to have peace. So not those candidates, but the serious ones. So you'll find that they will never commit mistakes in geomorphology because it is very straightforward. They will never commit mistakes in climate in oceanography. Very straightforward. No scope of twisting those questions. Right, oceanography. A couple of questions have been twisted recently, but not so much. Indian geography, the questions can be very factual, driven by current affairs, so significantly driven by current affairs that if you have been a good student, you have followed the portion of current affairs, maybe you will be able to do that. But some portions obviously will be out of your scope there. Climatology is that portion where you can create a difference, where you can make a difference with your competition. Because this is where even good candidates, they are weaker in concepts. Even for those good candidates, and I have come across many of them who basically they are very good in their general overall approach for geography, but some or the other portion of climatology is slightly weaker. So if you have good concept here, you will be able to create that difference. And particularly so in the mains examination, that is where you will be able, or you will have the chance to highlight your prowess. You will have a chance to highlight those particular concepts. And trust me when I say so, in our study for this portion of climatology, we will carry out the study to the deepest of the possible concepts, something that you will not always readily find to be present in your reference books also, which might create some anxieties out there that from where are you teaching this? This is not there in NCRT, etc. So be calm, be patient, and just ensure that you are paying attention on the slide in discussion. Once all this discussion has been carried out, then if you take a look at the larger picture, you'll find yourself to be in a much better position out there. Okay. So, with that approach, let us initiate the discussion for climatology and let us try to first of all understand the basics about our atmosphere and the basics about temperature also. Okay. So, here, when I talk about it, when we talk about the atmosphere, so atmosphere is what? It is the blanket of gases which surround the Earth's surface. Right? We don't feel atmosphere. We don't feel the presence of air around us. Whichever room that you are sitting in or sleeping in right now or standing in right now, regardless, you have air in that room, right? But you won't be able to feel that air. If you move your hand, your fingers around yourself, I'm sure air is not something that you feel. When do you get to feel or experience that air? When that is in motion, right? And also, basically, the pressure exerted by the air is also very high. So, the pressure that the entire atmosphere exerts on the ground surface is also very high. This is the reason why, when mankind, basically, or humans, when they go higher up in atmosphere, they have to carry with them special body suits or specialized pressurized cabins so as to ensure our body simply doesn't explode in the vicinity of low pressure air at higher altitude. But having said that, the extent of this atmosphere, now the extent of this atmosphere is said to be for thousands of kilometers up from the surface. But you have to understand, when we say atmosphere, maybe 200 kilometers up from the surface or 400 kilometers up from the surface, that is not the atmosphere that you experience here on the ground. On the ground, you have availability of a lot of air, oxygen, nitrogen, carbon dioxide. You breathe in, you breathe out, right? High density of air. But as you keep going higher up, the density of air keeps on reducing. And why is that the case? That is because as you keep moving higher up, you will come across a situation where the gases, they are present in lesser amounts because the gravitational force is lesser. So that is why majority of the gases of the atmosphere are very close to the ground surface. That is where the density of atmosphere is the highest, right? And there is no such end limit that this is the end of atmosphere. The gases are higher up, they are present in such less concentrations that eventually, as you keep going higher up, they will disappear and dissipate into the outer space. So this image that you see, this coloration that you see, this coloration is not of the ground surface at all. This bluish coloration pattern that you see is your atmosphere being lit up, right? So atmosphere eventually dissipates out there into the space, right? Where the gases basically they intermingle with the space. Now, when we talk about this atmosphere that we breathe in, that we live in now, that has not been created overnight. It is not as if, as the planet was created, you had this kind of an atmosphere in existence. No. Initially, when the planet was created, the atmosphere consisted of gases predominated such as hydrogen and helium. These are very light gases, right? Hydrogen, helium, they have one electron, one proton in the case of hydrogen, and two in the case of helium. So these are very light materials. So this was the case when the planet Earth was still in a molten state. Remember, in the evolution of Earth, we had talked about that at one point of time, planet Earth was in a completely molten state. It started solidifying later on, eventually, right? So, here also, at one point of time, when the planet Earth was in a completely molten state, you had the presence of gases such as hydrogen and helium, which were very light and were consistently shaved off by the solar winds, etc., which were a very regular phenomena in the unstable solar system, where very frequently the entire solar system would be blasted by a very strong solar wind. So all these events, they shaved off or they reduced the density of the atmosphere in early times, around 4.5 billion years back. But then, eventually, as the planet started cooling down, we came across a phase of degasification, where the planet went through hundreds and thousands and millions of volcanic eruption, sparking across the entirety of the planet's surface. Now, during that phase of degasification, you had introduction of new gases, gases such as ammonia, carbon dioxide, carbon monoxide, hydrogen, oxygen. These were released. Now, even here, even this point of time, amount of oxygen, etc., was very, very less, almost present in trace quantities. But then, almost around 600 million years back, you had the development of life. Life in the sense, you had the development of plants. Now, obviously, some primitive form of plants, etc., they came into existence billions of years ago itself. But the larger plants that we have, these angiosperms, for example, so these larger plants, they came into existence much later. And when these larger plants came into existence, they would carry out photosynthesis also. So, in the process of photosynthesis, what do you have? You consume in carbon dioxide, you produce oxygen. So all these plants, they started consuming the excess carbon dioxide which was present in the atmosphere, and they started giving out oxygen as a byproduct. Now, as a consequence of that, the proportion of oxygen in the atmosphere started increasing. The proportion of carbon dioxide in the atmosphere started reducing. Eventually, you came across a scenario where now carbon dioxide is lesser, oxygen is much higher. And this influences the life forms also. I don't know if I have said this before, but the proportion of these gases in the atmosphere to the varying degrees, they have the impact, or they will end up impacting the life forms that you observe on the planet also. When you had that sudden outburst of oxygen and the sudden presence of oxygen in large quantities across the planet, you had one of the most dominant of the dynasties which basically survived on the earth, were the most dominant of the species which made earth their own. And had it not been an asteroid collision, those dominant species would be still present on the planet's surface. We are talking about dinosaurs. So, if the level of oxygen in the atmosphere would not have increased around 350 million years back, 400 million years back, or 200 million years back, dinosaurs simply wouldn't have survived, right? So that is how. And even if the dinosaurs would basically think about it, if they would have been dominant, the mammals, they would have been restricted to the sidelines. So that is where even the evolution of life is dependent upon the evolution of atmosphere. Okay, so here when we talk about it, so evolution of atmosphere can be talked about in varying different phases. One is the earliest atmosphere. What is the primordial atmosphere or a primitive atmosphere? This was dominated by hydrogen and helium. Dominated by hydrogen and helium. Then evolution of new gases during the phase of degasification. Phase of degasification. So introduction of newer gases. Of newer gases like ammonia, CO2, CO, SO2, O2, H2, right? All these were produced. Now, mind you, nitrogen was introduced in the atmosphere at this stage itself, when you had basically the emission of ammonia. But nitrogen is not very reactive in nature. When you consider carbon dioxide or oxygen, they are very reactive in nature. They will react and interact with the rocks very frequently. But when you talk about gases such as nitrogen, they are not at all reactive in nature. So they tend to stay in the atmosphere as they are. Right. So that is why the proportion of nitrogen in the atmosphere has largely remained consistent, whereas the proportion of the other competing gases, they have increased or decreased over a period of time, but the proportion of nitrogen has remained consistent even today. Right. Even now, nitrogen doesn't react readily. Whereas when you consider carbon dioxide, for example, around the 95 million years back, that was the time. That was, if you consider the long history of the planet Earth, that was as recent as it can be. 95 million years ago, you had massive rate of volcanic eruption all across the planet. One of the most massive volcanic outflows that the planet had observed. Everywhere, materials were being brought up, right? Even in the continental areas, even in the oceanic areas, due to sudden release of heat from the interior. Now, during that period of time, underwater volcanic eruption was consistent and it was very high. It is that underwater volcanic eruption, by the way, which occurred around 95 million years ago, which created all these Caribbean islands, Iceland, certain portions around the portion of Atlantic, few islands which are created. So it was that underwater eruption, that phase. So during that phase, I don't know if you are aware or not about it, oxygen in the oceans were almost depleted, leading to massive die off of the species. And the oceans and the atmosphere also was predominantly rich in carbon dioxide. Suddenly, atmosphere became very, very rich in carbon dioxide. Now, that carbon dioxide in that great proportion, you would have thought that if it would have continued, what would have happened to the planet? But that carbon dioxide started reacting with the rocks, forming various carbonates. Right? Even today, when you have a lot of oxygen present around, oxygen reacts with the rocks, form oxides. So all the other gases, they react with the rocks, forming various compounds. But nitrogen tends to remain non-reactive. That is why even today, you will not find many rocks which are rich in nitrogen or which have any nitrogenous compound, nitrates, nitrites, etc. You won't find to be present there. Okay. So if the rocks themselves, they don't have nitrogen. So once the rocks, they weather off and they form soil, Will they have nitrogen in that case? No, they won't. This is the reason why almost all the soil types across the world, if you come across the soil types all across the world, you will find that almost all the soil types, they are poor in nitrogen. And that is the reason why nitrogenous fertilizers like urea, they are the most extensively used fertilizers across the globe and also across every part of the country. Be it the north or the south, east, west, central portion of country, anywhere you go, you'll find people applying urea. Urea enriches the soil with nitrogen. Why? Because the soil is poor in nitrogen. Why? Because the rocks did not contain nitrogen. Why? Because the nitrogen in atmosphere did not react with the rocks. Why? Because nitrogen in the atmosphere is quite significantly stable. Okay. Now, this continued for a substantial period of time. And then eventually you had the modification of atmosphere. Modification of atmosphere was carried out by the living species. Carried out by living organisms such as plants, and these plants basically, when we talk about it, by the process of photosynthesis. So they would carry out photosynthesis, which would utilize CO2 and produce O2. Okay, so that is basically the entire process of evolution. Here, UPSC has asked a question previously. UPSC had asked a question that when we talk about or the presence of oxygen has been there in atmosphere ever since the time of formation of planet Earth. Obviously, that is incorrect, right? And it was a kind of a multi-statement question that I will put up at the end of the week also for the general discussion in the session. So there, you also had a statement that the presence of organisms that has modified the atmosphere over the ages, which will be correct. So these kind of basic questions UPSC does ask. Now, when we talk about the evolution of atmosphere or the atmosphere in general, atmosphere consists of varying components, different components, such as water vapor, the presence of various different gases, and also the presence of dust particles. Now, before we talk about the role played by each one of them, I want to focus on the basics of greenhouse effect. I don't know how many of us are aware about the process of the greenhouse effect or the nature of the greenhouse effect or the greenhouse effect in general. I don't know how many of us are aware about it, but let us talk about this greenhouse effect and what is it, why the world talks about it, that due to greenhouse effect there's global warming, etc. Is it always damaging to the planet, or can it be beneficial to the planet also? That is something we are going to discuss very briefly here. Now, when we talk about greenhouse effect, it works on a very basic, simple fundamental. And the basic fundamental involved was, and what was the problem, first of all, was that in the regions of Northern Europe and Western Europe, during the winter, no crops could be grown. And in general, throughout larger parts of the year, crop growth could not be observed. Why? Because you had the situation where the nighttime temperature would fall so low and it would get so very low, the nighttime temperature, that majority of the plants and majority of the crops would simply die off. They would not survive, right? So, because the plants could not be grown outside, so what people did, they built a glass house, right? So a glass house was constructed. A glass house was constructed. And in this glass house, the plants were grown. The logic was very simple, that when you have the presence of this glass house, you will have you will come across the fact that the heat comes in, but the heat is not allowed to go out. Heat is retained by the glass surface. So that would lead to an overall slightly warmer temperature inside this glass house. And that would allow the growth of the plants. That was the basic principle. And based upon this principle, this was named as greenhouse because it would allow the growth of the plants. So this was known as the greenhouse. Right. Now, this similar property of the heat being retained and not being allowed to move out, that is being carried out by the atmosphere also. And that is what is known as the greenhouse effect. So, how is it or why is it that atmosphere allows the heat to come in, but some amount of heat it doesn't allow to escape? So, why is that the case? So, before that, some very basic portion that we will cover about, and this is about the greenhouse effect itself. The greenhouse effect overall. Now, what you come across as a situation, any object which is hot will release heat energy. Any object which is hot will release heat energy. For example, even if you switch on the nowadays you don't have those bulbs anymore, but I hope you remember the older yellow bulbs. If, even today in many of the households you will find those older yellow bulbs which used to glow. Now I understand everywhere there is tube light and the CFLs which do the rounds, but I'm sure you would have visited places where you would have seen those older yellow bulbs. Now, if you would switch on those bulbs for some time, right, they would become very hot, and it would simply burn your hand off if you put your fingers on that bulb. Now, even in that case, when the bulb has been switched on for some time, if you put your fingers or if you take your hand closer to the bulb, you will experience heat being released. So, what I'm trying to get at is the basic fact that any object which gets heated up will release energy, and object which gets heated up will release heat energy. Now, this is a common logic which drives or which flows from this is hotter the object, greater will be the energy released. Cooler the object, lesser will be the energy released. Right? So, this will form our first basic fundamental. Hotter the object, greater is the energy released. Cooler an object, lesser is the energy released. Now, we had basically had a conversation briefly during the time of talking about the geomorphology and seismicity itself. Energy travels in the form of waves. We do know that. Energy travels in the form of waves. There also, the seismic waves, they had the propagation where there also you had the existence of waves. So here also, when we talk about heat, this will also travel in the form of waves. Right? Now, the waves, they also, depending upon if it is a high energy source, the wave will be different. If it is a comparatively lower energy source, the wave will be different. When we talk about an object such as sun, right? Temperature is going to be very high. extraordinarily high, thousands of degrees Celsius. So can we say that the energy is very high? So very high amount of energy. Very high amount of energy. Right? So here they will, if someone has got very high amount of energy, energy will be released very frequently. Quite frequently, the energy will be released. So how will the energy travel? In the form of a wave, but in the form of here that energy will be released very, very frequently. Right. Whereas, if you consider, let's suppose planet Earth. Now, planet Earth gets heated upon receiving the heat from the sun. After that, the planet Earth also gains its heat. After that, the planet Earth also indicates a rise in temperature. So, once, let's suppose during the daytime, even today, I understand that winter is coming. So called the winter is coming in majority of the parts of the country. But still, daytime is very, very hot, right? So even today during the day, you observe that the temperature on the ground surface increases quite significantly. So throughout the day, when the ground surface gets heated up, it will also start releasing energy because that now it will also start acting like a hot object. So when the ground surface releases energy, can we say that it has got the same level of energy as the sun? Obviously not. Sun is at thousands of degrees Celsius. Ground surface is at your 30, 40 degrees Celsius. Ground surface is much cooler. So the earth also releases energy, and the energy that has been gained from the solar heating. So the earth's surface, after getting heated from the sun, also starts behaving like a hot object, and that also starts releasing energy. But that energy released by the earth will be slightly lesser. So it will release that energy ever so slowly. So here, when we talk about earth, here releases energy in a different format because it has got lesser energy, obviously because of much lower temperature as compared to the sun. So that will be the case. So here, if you observe these waves, right? So here, let me write it down. Lower amount of energy is released. So here, if you observe these waves, their shape is different, right? The waves coming from the sun, you'll find that they have a very shorter wavelength. What is a wavelength? When you consider any particular wave like this, when you consider any particular wave like this is your wavelength, the length of a wave. So that is considered to be wavelength. So here again, in the portion or the wave emitted by the sun has got very shorter wavelength. Why? Because of high level of energy. So these are known as short waves. Short waves. Very high amount of energy. Those from science back, this I am describing for those from non-science backgrounds. This description is not for those people who have science background because you would have read it multiple number of times already. So non-science background candidates, this is That is why I'm trying to simplify it as much as possible so that you associate it with logic. You don't ascribe it that, okay, this is that particular principle driven by Stephen Boltzmann law, etc. Don't complicate it. Just drive it from the simple logic. Higher energy, energy will be released very frequently. Lower energy, energy will be released slowly and steadily. So when the energy is released so slowly and steadily, observe the length of the wave also. The length of the wave is large. So these are what are referred to as long waves. Okay. Now, long waves. Basically, the wavelength is quite significantly longer in this case, larger in this case. Obviously, less energy. Now, when we consider the planet, when we consider the planet Earth and the atmosphere thereby, let's suppose this is the atmosphere. So when the solar waves come in, the solar rays, when they come in, so that comes in the form of the short wave radiation. Okay. These come in the form of short wave radiation. They will heat up the ground surface. And because they have a short wave high energy, they will be able to penetrate to the atmosphere also. Now they will heat up the ground surface. Once the ground surface heats up, it will also start behaving like a hotter object, but this will release long wave radiation. So this will release long wave radiation here. But because it is of low energy, some amount of that, even though it will manage to escape some amount, but majority of it, because it is of low energy, will be trapped by the gases in the atmosphere, will again lead to reheating again. So like that, heat will be retained. Okay, so this is the wave which is released, or the energy wave released from the Earth's surface, the radiation released from the Earth's surface, that is also referred to as the terrestrial radiation. So the energy waves, this is what is known as the long wave terrestrial radiation. A long wave terrestrial radiation is what you will observe, what you will experience here. So, in this case, the atmosphere retains the heat, okay, because the long waves, they are not allowed to escape. And this is similar to the greenhouse concept that we had studied. That is why this is referred to as the greenhouse effect. Now, traditionally and ideally, greenhouse effect is beneficial for planet. Why? Because if the greenhouse effect, or if this heat retention would not have been observed, imagine a circumstance where during the daytime, the temperature would have been high around 50, 60, 70 degrees Celsius. But during the night time, because none of that heat has been retained, during the night time, the temperature would have plummeted to minus 100, minus 200 degrees Celsius. For example, what we observe in the case of moon. What do we observe in moon? During the daytime, during the lunar day, the temperature is still tolerable, but during the lunar nights, the temperature dips to minus 100 degrees Celsius and even lower. Similar is the case with many of the planetary systems as well, where during the daytime the temperature is very high, but during the nighttime the temperature is very, very, very low, right? So, this retention of heat, which is done by the atmosphere by what is known as the greenhouse effect, that allows the planet to maintain its temperature and retain the temperature even during night time. Because during the day you will experience around 30 degrees Celsius, during night you experience 20, 25 degrees Celsius, isn't it? That means heat has been retained. So that is where it is instrumental here. But then, if let's suppose certain gases, such as carbon dioxide, certain gases such as nitrous oxide, sulfur hexafluoride, methane, water vapor, all these gases, they start dominating the atmosphere, as we have been observing since the time of the industrial revolution. What tends to happen is that none of this heat is allowed to escape at all the heat is being retained. So that is what is leading to heating and warming of the planet, which is a slight departure from the usual rate. That is why we say that increased carbon emission has led to an increased greenhouse effect, and that has led to global warming. Okay, so when we talk about the case of the greenhouse effect, so it is the short wave, or simply we can start by high energy short wave solar radiation gets through the atmosphere and heats up the earth's surface. Then, after the earth's surface has been heated up, earth releases low energy terrestrial radiation which is trapped by the atmosphere retaining heat on the surface on the planet even during night. Right. So, what you observe in this case is that the terrestrial radiation, basically, the Earth also tends to, when the Earth has got some amount of energy, some amount of heat, it will also end up releasing that heat, and Earth cools down also by releasing that terrestrial radiation. Earth will release that terrestrial radiation. Why it is terrestrial radiation? What is terrestrial radiation? So, in simplest of the terms, it is the energy which is released by the Earth's surface. After receiving the heat from the sun, Earth will release that energy or will lose that energy. So, because that energy is released in the form of waves of radiation, hence the term radiation, and because it is originating from the terrain, hence the name terrestrial radiation. So, that is the process by which the Earth, over a period of time, also cools down during the night, etc. So that is the case of greenhouse effect. Now here, this greenhouse effect is carried out by the presence of various different gases. So here, when we talk about the composition of the atmosphere, each of these, be it the gases, be it the water vapor, be it the dust particles, each of them have their own unique role that they end up playing. For example, when we talk about gases here, gases basically refer to, or the various different gases such as nitrogen, carbon dioxide, oxygen, etc. So the gases, they become our providers of life on planet. right? It is the availability of these gases that we are able to breathe. If these gases would not have been there, we won't have been able to breathe at all, right? And here you will observe that these gases, they also play a substantial role. Not all the gases have the property to retain that terrestrial radiation, but some of the gases such as carbon dioxide, etc., they have the ability to retain heat, right? So they facilitate greenhouse effect, and that is how they ensure the retention of heat by the planet even during night time. So gases such as CO2, etc., or simply, let's talk in general nature itself, retain heat released by Earth during due to terrestrial radiation, due to terrestrial radiation and help maintain the temperature of the planet even during night. Okay, so these gases are very instrumental in ensuring. It is a different matter altogether that over the past few hundred years, ever since the time of the Industrial Revolution, we have come across a situation where the proportion of certain gases such as carbon dioxide, etc., have quite significantly increased in the short term. And as a consequence of this, they have a greater ability to retain the heat. Not all the gases will have the same property. It is not as if methane will have the same property to retain heat as carbon. It is, or carbon dioxide. It is not as if, for example, nitrous oxide will have the same property to retain terrestrial radiation as, let's suppose, any other gas like sulfur hexafluoride, right? Because of the various different molecular structures, the bands, etc., which are present, how they appear together. So that is why different gases have a different ability to retain heat. When we talk about carbon dioxide, etc., their emissions have increased over the past few hundred years. Their concentration in atmosphere has increased. So in those areas, there's a greater retention of this heat, the terrestrial radiation. So that has led to increased level of warming also. So if carried out in excessive proportion, greenhouse effect can lead to global warming, but otherwise it is very beneficial, very helpful for the planet, allowing for the plants to exist during the night time, right? So when we talk about the perfect conditions to prevail for the existence of life on the planet, so many areas, many different parts of the planet, many different planets also have many conditions which are similar to the Earth's surface. But it is these nuances, that is during nighttime, the temperature, let's suppose on planet Earth, during nighttime, if the temperature would have plummeted to minus 50, minus 100 degrees Celsius, the plants would never have been in existence at all. Many of the life forms would never have been in existence at all. So it is that maintenance of heat even during nighttime which allows the growth and the availability of life, right? Then you have the water vapor. Water vapor is also a gas, by the way. It is the gaseous state of water, right? So, water vapor plays a very instrumental role in influencing the climate around us. Cloud formation, thunderstorm, hailstorm, snowfall, rainfall, cyclonic formation, all these events, monsoonal events, all these are contributed by what? By water vapor. Water vapor, all the water vapor which is present in the atmosphere is largely concentrated very, very close to the ground surface. And it is in the lower levels of atmosphere itself where you will find the highest concentration of water vapor. And the reason is very simple. The Earth's gravitational pull is the strongest attraction force. Now, the Earth's gravitation that is around the planet, it is the strongest attraction force. So, the Earth's gravitational pull attracts all the gases, and that is why the concentration of gases is going to be highest near the Earth's surface. But if you consider all the water vapor which is present in the atmosphere, if let's suppose you were to condense it somehow, you had God had given you that power that you can condense all the water vapor present in the atmosphere, the entire planet would be covered in water, but not a very thick layer of water. A water maybe having a thickness of half an inch or 1 inch. So that tells you that the amount of water vapor in the atmosphere is not very high. And that too is restricted only into the lower layers. But that in itself is more than sufficient to bring about the cycles of rainfall, cyclones, all these events that we encounter. So, here, when we talk about the water vapor, basically climatic events like cloud formation, cyclones, etc. And then water vapor also acts as a potent greenhouse gas. In the sense, it also has the ability to retain heat. So, also acts as a potent greenhouse gas. And retains heat. Closer to surface. Now, in the atmosphere, you also find the availability of dust particles. Just like water, the dominance or the concentration of dust particles is also something that you find very close to the surface itself. Right? That is where majority of the dust particles would be found to be present. Now, when you talk about the presence of these dust particles, they also solve multiple purposes. One of the basic purposes that the dust particles solve is the fact that if you recall during your own lifetime, your own past experiences, the darkest of the nights, when let's suppose you encountered a situation where there was no moon, right? Moonlight was not available, right? And there was no artificial light in that area also. You must have experienced that scenario sometime or the other in your life, maybe in your rural area or in a native place, or maybe you were exploring a region or in a mountainous area. You would have experienced this sometime or the other. Even during the darkest of the nights, if you recall, you're not completely blinded, are you? You will still be able to figure out that, okay, this is a tree, or these are many trees together here, so that might be a forested area, this might be an open space. You're able to figure that out, at least distinguish some of the basic shapes and forms. How do you think that is possible? When the light is not available, when the sunlight is not available, the light from the moon is not available, still you are able to see. Why? Is it because God has blessed you with some kind of vision which will help you look through the darkness also? No. It is because during the daytime, when the solar rays were coming in, many of these dust particles, they scatter the solar rays. And as the solar rays, they get scattered and spread over, they get trapped within some part of that energy, gets trapped within the dust particles themselves. And that energy is released during the night, what is referred to as diffused light. And that diffused light, again, provides light during the darkest of the nights that helps us to see during the darkest of the nights. So by scattering of light and by trapping of light of the sun, these dust particles allow us to see during the darkest of the night. Now, this is one of the role played by dust particle. other role played by dust particle is much more important, even more important than many of the different contributors to atmosphere. That is rainfall. If I tell you that rainfall would not have been possible had the dust particles not been present. Now, why is it so? Because of the basic phenomena, which we will touch upon at a later stage also. Rainfall happens why? Because of cloud formation. Without cloud formation, no rainfall. But cloud formation, what is a cloud? Again, don't panic. I will cover the entire formation of cloud in detail in the next few modules also. But cloud formation, whatever basic idea that you have till now, I'm sure nobody till this point of time in your life, I'm sure nobody would be believing that it is the angels and the fairies who create those clouds. I'm sure we are aware that the water vapor in the atmosphere condenses, it cools down to form these clouds, right? But condensation can never take place without a surface. Anywhere, condensation requires a surface. For the conversion of water vapor into liquid water droplets or water vapor into, let's say, solid ice particles, it requires a surface. Who provides that surface in the atmosphere? It is the dust particles. It is these dust particles which are present where, and because they are present higher up in the atmosphere, they are very cold. So water vapor, when it get the gaseous particles of water, when they get in contact, they immediately cool down and they form a small droplet of water in the dust particles. Many such droplets, they are suspended together and they form these large clouds that you see. So had these dust particles not been present, you could not have experienced the rainfall as it happens. So that is why the role played by dust particles are also manifold. First of all, by scattering and trapping solar energy. They emit diffused light, allowing us to see during darkest of the nights. And also, they form the hygroscopic nuclei. So you have certain types of particles which don't allow the presence of water on top of them. They will repel water. They are known as hygrophobic. They won't allow the presence of water near them. Many of these dust particles, they act as hygroscopic, where they allow the water droplets to form on top of them. That facilitates condensation. So act as hygroscopic nuclei and facilitate condensation and eventual cloud formation. Eventual cloud formation. So that is the contribution of each of these different components of the atmosphere. Now, generally, you will find that if you consider the atmosphere, maximum density of atmosphere is observed closest to the ground surface. Why? Because of increased gravitational pull of attraction. That is why the density of atmosphere is highest closer to the ground surface and reduces as you move higher up. Okay, so we'll build on that concept furthermore, and we basically talk about it after a break. So we take a break right now. We'll take a 10 minutes break and we'll be back after 10 minutes. Okay, see you in 10 minutes. A confirmation about the audio, please. If the audio is clear and available, kindly confirm. Thank you. Thank you, Seema, for the reminder. We'll keep that in mind. Now, here we move ahead with the remaining portion of atmosphere as we will go ahead. Now, we have talked about the fact that the atmosphere consists of various different gases. So, amongst the various gases included in the atmosphere, you have the presence or the predominance of a gas that is nitrogen. Nitrogen is the most predominantly available gas out there into the atmosphere. And then you have oxygen, argon, carbon dioxide, and so on. So here, ideally, you don't have to memorize or rote learn the exact percentage or the exact proportion of all these gases, but it is always advisable to remember the top four, because majority of the candidates, when they think about it, they are aware about that nitrogen is the most dominant, followed by oxygen, but then the third gas, they always come to a conclusion that the third most dominant gas would be carbon dioxide, but that is not the case. The third most dominant gas is actually argon, followed by carbon dioxide. So that is basically your proportion of gases, while the other varying gases such as oxygen and carbon dioxide, their proportion have been increasing and decreasing for the geological past of the planet, but the proportion of nitrogen has largely remained consistent. And that is because of the fact that nitrogen does not react very readily. Nitrogen doesn't interact very readily. Okay. Now, but this is again going ahead into the future. This again is prone to change. Now, then we come to the modes of heating. So, what are the various different modes of heating? See, I see many of you pointing out that the break time has been exceeded. Fair enough. Please understand, if there are 2 or 3 minutes, if extra break time has been given to you, has been provided to you, or a slightly maybe 2 minutes lesser break time has been provided to you, that should not be a make or break. You are here to learn, right? You are here to learn over a 3.5 hour period. So if that 5 minute problem, 5 minute induces that much amount of a problem, please put that to our attention, write to us, we'll take care of that. But then it shall be considered moving ahead into the future. Now, when we talk about modes of heating, so you have varying different modes by which the atmosphere gets heated up. So when we say the atmosphere getting heated up, how is it that the atmosphere receives that heat? So basically, heat is emitted from the sun, right? Now, the solar rays, they end up traveling through almost vacuum of the space for close to around 150 million kilometers. And then they end up reaching the Earth's surface. Now, that is a mode of heat transfer, which we refer to as radiation, right? The solar rays, they heat up the ground surface upon reaching the surface. Now, in the meanwhile, when we talk about the solar rays, they pass through the atmosphere also. But their impact on atmospheric heating is not very significant, right? Why is it so? And listen to this carefully again. The solar rays, when they are incoming, even though they have a very high amount of energy, they don't immediately end up heating the atmosphere. Why? Because atmosphere is in gaseous state. When we talk about solid, liquid, and gas, I hope we are aware that as a state of matter, gas is the most inefficient medium for heat travel or heat transfer, because you will have various different particles, various different molecules which are far away from each other. Okay, so various different particles or molecules which are far away from each other. Now, in case, let's suppose the solar rays, they are coming up, it might heat up this particle, or this particle might even escape from that area, right? So gases, they don't get heated up effectively by the solar insolation, at least not closer to the ground surface. So the solar insolation or the solar radiation, they actually end up heating the ground surface. The ground surface gets heated up. Once the ground surface becomes hotter, then the air particles, the air molecules in contact with the ground surface, the air molecules in contact with the ground surface, they will get heated up. Okay? Those air molecules in contact with the ground surface, they will get heated up. Now, once these air molecules, they heat up, then what will happen? They will, in a way, means that this particular air parcel or the sample of air that we are considering, this has gotten heated up. Means what? It means it will have higher amount of energy. All the particles will have that energy. Many of the particles might even escape the system. Many of the particles might move away from that particular system. Many of the molecules, they have so much higher energy, they move significant distance away. So this particular air sample or air parcel, as compared to earlier, now that it has gained energy, particles would have escaped. So this air parcel would become lighter and it would rise up. And then it would spread the heat, distribute the heat in the upper portion of atmosphere, just like how convection would do in the case of a liquid. We have seen that when you heat a liquid, it is basically the base of that liquid which gets heated up first. But then that motion is initiated, a convection current is initiated within that entirety of the portion of the liquid for that transfer of heat. So for the heating of atmosphere, for the heat present in the atmosphere, you have different modes of heating which are involved. First of all, it is the mode of radiation by which the solar rays, they end up heating the ground surface. After that, then the ground surface heats the air directly in contact with that by the process of conduction, right? And then eventually, by the process of convection, that heat is circulated in the atmosphere. So, heating of atmosphere, when we talk about here, solar radiation heats the surface, ground surface, okay? Then ground surface heats the air in contact, and then heated air transmits the heat to the surrounding by process of radiation or process of convection rather. They tend to transmit that heat by the process of convection, and that is how the heat is retained. Okay. Now, that means logic tells us closer that you are to the ground surface, hotter it will be. Higher up that you go from the ground surface, it will get cooler. Isn't it? Why? Because the source of heating for the atmosphere is the heat released from the ground surface, the heat attained from the ground surface. So that is a general phenomena that you come across, where you will observe that closer to the ground surface, there is a higher amount of heat. Higher up that you go, it tends to become cooler and cooler. Now, there is another mode or another method of heat transfer. from one region of the planet to another, there is a mode of heat transfer which we refer to as advection. So you would also have experienced that during the or maybe during the summer season when it is very, very hot, very, very warm, suddenly a cool wind blows, and that cool wind basically cools down the conditions. It becomes very pleasant. During the winter, sometimes it is very cold, and suddenly a warm breeze blows over, and suddenly it moderates the temperature, isn't it? So, that horizontal movement of hot and cold wind, that also plays a substantial role in modifying or in facilitating heat transfer. So, that process of heat transfer through the horizontal movement of wind, that is what is referred to as advection. So when we talk about advection, transfer of heat to the horizontal movement of air, that is advection. So that means all the winds that you have experienced in your life till now, all the various different types of winds that you have experienced in your life, that is nothing but a form of advection, right? Many of you would not have come across this terminology before. So advection is when the winds, let's suppose a region here, let's suppose this region is cold, this region is warm, okay, and the wind blows from here to here, it will cool down that particular region, right? So that is the example of cold advection. Then you also have a situation where, let's suppose, the reverse of it actually. So you have a warmer area and you have a colder region. So you can also come across a situation where from here winds will blow. Now, in that case, when winds will blow from a warm region to cold area, now that will create a colder, or this will warm up this region. So this is the example of warm advection. Example, Lu, that we experience. In the northern part of the country, you experience this very hot and dry wind during the summer season in the afternoons. That is an example of warm advection. Okay, so this is basically the process of advection, which is also instrumental in terms of heat distribution from one area to another. It is of two types. It is cold advection and warm advection. When we say a cold advection, process in which the wind blows from a region of a cold air to a region of a warmer air, which results in cooling off the warmer region. And when we talk about warm advection, process in which wind flow blows from a region of warm air to a region of cooler air. So that is basically another mode of heat transfer. Across the entirety of the planet, you have a situation, as you will come to appreciate as we move ahead in these modules, that the regions of the lower latitudes, and by this point of time, another thing, another terminology I want you to get very proficient at is the aspect of latitudes. When we say lower latitudes, we always mean the regions closer to equator. When we say higher latitudes, we mean the region around the poles. Why? The poles have a latitudinal demarcation of 90 degrees. Closer to the poles, higher latitude. Mid latitude, that is the region around somewhere 40 to 60 degrees north and south of equator. That is mid latitudes. Again, you will hear about the term tropical, temperate, and polar also. So tropical, the region lying between the Tropic of Cancer and the Tropic of Capricorn, right? So that region is considered tropical. Beyond that, it is considered extratropical also, right? Then in the region around 50, 60 degree, etc., 45 to 65 degrees, that is referred to as temperate region of the world, where you have moderate climatic condition. And then closer to the poles, frigid zone, polar zone, frozen zone. Okay, so these are the references that you will come across as we move ahead with the module, and every time that we come across these, you will obviously be able to understand that without any issues. Now here, When we talk about this process of advection, many of the times that is much more important in distribution of heat from one region of the planet to the other. For example, when we consider the regions of lower latitude, that is the region around equator, over a period of the entire year, if you take on an average, that is the region which receives very high amount of heat. Okay, whereas the polar areas, they tend to receive considerably and comparatively lesser amount of heat. So that is why you have the lower latitudes which are in a position of a heat surplus, and you have the polar areas which are in the condition of a heat deficit. So that transfer of heat from the heat surplus to heat deficit regions of the planet, that does happen, that is facilitated by this process of advection itself. Okay. Now, another basic concept that we are going to cover here is that of a lapse rate. What is lapse rate? So basically, it is the rate of change of temperature as one moves higher up in the atmosphere. How is it that the temperature is changing? Because the temperature won't be consistent closer to the surface, and even if you go 100 kilometers up from the surface, it is not going to be the case that the temperature tends to remain consistent. It will end up varying, isn't it? So here, when we talk about lapse rate, what is it? It is basically how the temperature changes as you move from one height to the other height. Now, there can be three possibilities only. That first, temperature remains consistent, does not change with height. One possibility can be that temperature reduces as we move higher up. Other possibility can be temperature, in fact, increases as you move higher up. So accordingly, you have the classification of lapse rate as well. So here, when we talk about it, you have the condition of positive lapse rate, negative lapse rate, and zero lapse rate. How wind blows from warm area to cold area, just like the wind blows from cold area to warm area. What is the doubt in that? Why can't the wind blow from a warm region to a cold region? Or are you one of those smart candidates who has studied about pressure already and is trying to highlight that particular knowledge here? Are you amongst those? Okay, I got that idea. So obviously you have not studied about pressure comprehensively. So when you consider westerlies, they blow from the tropical region to the temperate regions of the world. They are the example of warm advection. When you talk about Lu, it is an example of warm advection. When you consider Chinook, it is an example of warm advection. When you consider Phone, it is an example of warm advection. When many of the winds, I can give you the example, which are example of warm advection, where the winds originate from the warmer areas, move to the colder regions. And that is because they move from high pressure to low pressure. Because now that you have studied pressure, that is why. So they move from region of high pressure to low pressure. And if you have studied pressure, let me confuse you even more. Regions of warm air can also be the regions of very high pressure. Region of cold temperature can be a region of low pressure also. Okay. So when we will come to it, all the intelligent people out there, all the very super smart people out there, when we will come to it, we will cover that in detail. But as of now, have patience. Whatever is being covered, I understand that it might be below the intellectual level that many of you have reached. I understand that you require a greater amount of intellectual stimulation. Till that point of time, try to have patience, try to keep up with the rest of the class. We will come there, and then we will be talking about how winds will move from a warm region to a cold region, what is a thermal pressure belt, why that is created, in which parts of the planet do these thermal pressure belts they get into existence. Okay, so that is for all the smart people. Okay, no offense meant. But UPSC requires the general average aware graduate. So we are going to consider it as an average session as we continue. Okay. Now, now we come to the portion of this lapse rate back again. And when we talk about this lapse rate, this is of three types, depending upon how that temperature will vary. As you move across the height, you will come across a situation that a temperature can decrease, the temperature can increase, or the temperature in certain cases can remain consistent also. And you have these conditions prevalent in different parts of the atmosphere. We'll talk about it moving ahead also. So, what they are is basically the, in this case, you observe a reduction, decrease in temperature with an increase in altitude. Negative lapse rate is increase in temperature. Chandrajyoti, by the way, and sorry for the rest of future, I received the mail that you had sent about the plate tectonics, and there it is very detailed explanation that I will need to provide in order to you. So basically, for rest of the session, to just provide you a context, Chandrajyoti had asked a question that in NCRT it is given that the Indo-Australian plate, that is the eastern part of it, is referred to as a spreading site, a site of divergence. Whereas what we have studied is that the Indo-Australian plate on the eastern side is converging with the Pacific plate. Okay, so that is one of the confusions that basically a couple of you had pointed it out. So just a brief idea that I will give it to you, that at the region to the east of the Indo-Australian plate, to the east of Australia, you have the region of Tonga convergence, the region around the Tonga Islands. Now, in the region around there, because the Pacific plate has been subducting to such a rate, you have a small Tonga plate which has also been created, a very small Tonga plate. And that Tonga plate is basically experiencing, on one side it has the Australian, on another side it has the Pacific plate. So on the side of the Australian plate, that is where marginally it is in a spreading site. So going ahead into the future, Tonga plate will come out to be like that of a Nazca plate. That is why eastern part of Australia is referred to as a expanding site. It is across that area that you have the Travera eruption, the example of the volcanic eruption that we had cited. Okay, I hope that is understood, Chandrajyoti, and for the rest of you as well. Now, this is the case of negative lapse rate, where we have an increase in temperature with an increase in altitude. And then zero lapse rate. Zero lapse rate indicates no change in temperature, change in temperature with height. So these are the different changes in temperature that we experience in different parts of the atmosphere during different times of the year also. Mostly, we experience the fact that the heating is received closest to the ground surface. It is the ground surface which gets heated up, and then the ground will heat up the air above it by the process of conduction, and that air will then rise up and will heat the surrounding by the process of convection. So that is why mostly we'll come across a situation where the temperature is highest closest to the ground surface and reduces as you move higher up. At least in the region closer to the ground surface, we come across what is referred to as a positive lapse rate. And there are reasons why positive lapse rate is experienced. We'll come to those reasons. But first of all, I want you to understand and internalize the very basic concept that the density of atmosphere is maximum where? Atmosphere. Yes, Rohit, that is correct, but I'm referring to something else. Is maximum closest to the ground surface. Correct. And that is because of the fact due to the influence of gravity. Influence of gravity. Right? This basic concept I want you to internalize. That the number of air particles, water vapor, dust particles, everything that will be maximum closest to the ground surface, its concentration will start reducing as you move higher up, and that is purely because of the impact of the force of gravitation. Okay, now here, before we move ahead, I want you to understand the concept of this lapse rate, and we will cover this in slight detail. As of now, we will cover the portion of positive lapse rate only. Why is it that the temperature reduces with height? So, when we talk about positive lapse rate, reduction of temperature with height. But why does this happen? This happens because of two reasons. The first reason being that closest to the ground surface, it is the heat received from the ground surface that is transmitted higher up by the movement of air, isn't it? So, closer you are to the ground surface, greater will be the amount of heat. As you move higher up away from the ground surface, lesser will be the amount of heat received, isn't it? So, that is why closest to the ground surface, you experience higher temperature. So, in this case, there are two reasons. First reason, as heating of lower layers are carried out from the ground surface farther away that we move from the surface, cooler it gets. Right? So, farther away that you move from that ground surface, from the source of heat, it will get cooler over a period of time. There is another reason. Greater number of particles present closer to the ground surface means what? That there will be greater amount of retention of heat as well. Right. So when you have greater number of particles such as water vapor, for example, we have seen that water vapor is able to retain heat. So greater number of particles that you have closer to the ground surface, there will be greater amount of retention of heat also. So greater number of particles, gases, water vapor, etc. means there is a greater retention of heat. Of heat. Hence, the lower layers are able to be warm and upper layers or upper regions are colder. So this is again a reason why as you move higher up in altitude, the temperature tends to reduce. Under normal, now this is not going to be consistent, that even in the case of Delhi, as you move higher up, you will have the same rate of reduction of temperature. Even let's suppose in Boston, as you move higher up, or in let's suppose New York, as you move higher up, you will have the same rate of reduction in temperature. That is not consistent. It tends to vary from one region to another. That is varying, but and it is dependent on many of the local parameters as well. But in general, on an average, we say we can observe in general under normal conditions that on an average the temperature reduces by almost 6.5 degrees every kilometer that you move higher up. The temperature would reduce by 6.5 degrees Celsius. So that is what is also referred to as the natural or a normal lapse rate, or what is also referred to as the environmental lapse rate. So under normal conditions, normal conditions, temperature reduces by 6.5 degrees Celsius per kilometer. So this is your what is known as environmental lapse rate, or a normal lapse rate. Okay, so that is the case observed. So here, environmental lapse rate is what? It is the rate at which the temperature changes with an increase or a decrease in altitude. If the lapse rate is positive, the temperature decreases in with height, as it usually does. But under certain conditions, excuse me, under certain conditions, the temperature tends to increase with height, and that is the known as the condition of temperature inversion. When we have the situation where the temperature basically tends to increase with height. So those are certain very unique conditions that we will study separately under the process of temperature inversion. Okay. Now, all this that we are referring to, we are generally referring to the lower regions of the atmosphere in itself. Now, here another concept that I want you to understand is the fact that in different areas, this lapse rate is going to be very, very different. For example, when we consider a region which is having high amount of water vapor or moisture, so in that area, what will happen? So let's suppose I give you a comparison of two areas, right? A, which is across a coastline. Let's suppose this is across a coastline, or let us be much more specific in that. Let's suppose I'm talking here of Jaisalmer, midst of the desert, and let's suppose I'm talking about Goa, the festive location and basically the coastal area. So obviously the amount of water vapor in Goa would be very high, right? The water vapor concentration in Goa would be very high. But before everything else, I want to see how good you are in that calculation. I want to have that. If I have a ground surface temperature of 30 degrees Celsius, as per environmental lapse rate, if I move up 2 kilometers, what will be the temperature at the height of 2 kilometers? 43 degrees Celsius. 17 degrees Celsius. Yes, it is 6.5 degrees per kilometer. So it will be here 17 degrees Celsius. Right. That is generally what is observed. Right. Temperature reduces in general. So we have also talked about another basic fundamental, that when you have water vapor also behaves like a greenhouse gas, that also retains heat. So it will retain heat for a longer period of time. Now let us consider two places, Goa and Jaisalmer. Goa has got lots of water vapor. Vapor concentration is very high, right? Lot of moisture, lot of humidity will be present in Goa, whereas in Jaisalmer the air will be very dry, as you observe in the case of a desert. Now, if let's suppose the temperature in both these areas is 35 degrees Celsius. Now, if I talk about the height of 2 kilometers in both the cases, will the temperature be the same at 2 kilometers high up in the atmosphere from in the region of Goa and the region of Jaisalmer? Would the temperature be the same? Well, if the temperature would have been the same, I would not have put up this question, in fact. So the temperature obviously is not same. Now, out of this, where do you think greater amount of heat will be retained by the atmosphere, by the air? Where do you think the air will be warmer at a height of 2 kilometers as compared to each other? Very good. It will be in Goa. In Goa, the air will be warmer. It will be able to retain heat, isn't it? Why? Because you have a very high amount of vapor which is present. Whereas in Jaisalmer, you will observe that you don't have that many amount of water vapor particles. Air is dry. So if water vapor is not there, remember, more number of particles means greater retention of heat. So heat won't be retained. So that means heat will be lost very quickly, isn't it? Whereas in Goa, the heat will not be lost because all that water vapor, it will trap that heat, it will retain that heat. That is why during the nights in the deserts during the nights, the temperature drop very significantly. The deserts, they might be very warm during the day. Few of them, the hot deserts actually might be very warm during the day, but during the night, they become extraordinarily cold. And that is because the air above the deserts is so very dry. It doesn't have water vapor at all. So it loses heat very quickly. Whereas in the coastal areas, you will find even nighttime temperature is hot and humid. So that basically tells you that the lapse rate tends to vary if the conditions are moist, if the conditions are dry, the lapse rate tends to vary. That is why in the moist conditions, generally the lapse rate is somewhere around 5 degrees Celsius per kilometer. 5 to 5.5 degrees Celsius per kilometer is the lapse rate under wet conditions. Wet as in moist conditions. Whereas in the dry regions, the lapse rate can be as much as 10 degrees Celsius per kilometer under dry conditions. Right. So 2 kilometers higher up in Jaisalmer will give you a much lower temperature as compared to 2 kilometers higher up over the region of Goa. Okay. So the presence and the availability of water vapor also influences this lapse rate. Okay. Now, Then, when we talk about the process of loss and gain of heat, you have another process which basically talks about the atmospheric and different parts of atmosphere gaining and losing heat in the process, and that is adiabatic process. Adiabatic process is something again that we would surely have experienced at some or the other time in your lives. Now, what is this? So, till now, we have seen that the air becomes hot or becomes cold when you heat it up, when you cool it down. When you provide that heat source from outside, it will heat up. When you provide that colder source from outside, it will cool down. Right? That is something that we have seen. But sometimes the air temperature tends to vary purely by virtue of the change in volume. If I have an air sample in front of me, which is this big, if let's suppose I compress it by some means or another, or if I expand it by some means or another, so I'm changing the volume. So by virtue of that change in volume itself, the air temperature varies. And that is what is referred to as the adiabatic process of heating or cooling. Now, nowadays, you don't. So, the easiest example of that could be the bicycle pumps, the pumps with which you fill air in your bicycle tires. But now the bicycle tires have changed. You have tubeless tires, and even the pumps have changed. So, that example doesn't become relevant anymore. But even still, despite that fact, I'm sure we must still have few of the candidates amongst here in the entire session who would have still filled up the bicycle tires with the older kind of pumps that you had, where you had to pull in and then compress, then again pull in and then compress. So, in those pumps, what the experience would be that if you carry out that process of filling the air continuously, after 5 to 6 such compressions of the pump would start heating up, right? Because compression of air would happen. So, when you compress the air or when you expand that air, there is a change in temperature which is experienced, and that is adiabatic process of heat gained or lost. Now, why does that happen, or how does that happen? So I want to provide you a kind of an analogy. Now, relate to the school classroom. Generally, it is in school that we are in that childhood phase where we have a lot of that energy and a lot of that noise creating ability, right? So remember those school days. Now let's suppose you were sitting in a classroom, and your classroom ideally had the size for 45 students, let's suppose. Now, if all those 45 students obviously were sitting in the classroom, there would be a lot of noise, regardless of whichever school that you have studied, for how much duration you have studied, whichever part of the country that you have studied. Almost every school you experience the same complaint from the teachers that the school is very noisy. Please shut down, or please shut up, in the sense that you're creating a lot of noise, etc. Because the noise levels in the classes are always generally very high. But what if from this classroom, all the 45 students were then accommodated in a small storeroom of sorts? Now, what would have been the noise level? When you bring all those students together into a further smaller room, what will be the noise level? Much higher, right? All that noise will accumulate, it will be much more higher. So, we can see that the energy level in a way has increased. But if I take the same number of students, take them into a larger field, and I ask them that go play in a larger playground. Now, when they play in a playground, you won't be able to hear the conversations that few of the people are carrying out, etc. The noise level will drown out. Why? Because now that energy has been spread over a larger area, right? So the overall energy level has come down. So that is why you won't hear any noise at all. Similarly, when we talk about, let's suppose, the case of air parcel. So let's suppose I have an air parcel here. Now in this, I will have various different molecules, just like the students in the classroom. Now, here, if I were to somehow compress this air, compress it. Now, if I were to compress it, all these particles have to be fitted here. All these particles will try to get accommodated here itself. Isn't it? All those particles will try to get accommodated here itself. So within these particles, amongst these particles, the number of collisions which will happen, the number of collisions will increase, right? That will happen. As amongst these particles, all of them are compressed into a smaller space, the number of collisions which will happen will always tend to increase, will be bound to increase. So here, the number of collisions increases. Each collision produces some energy, so energy level increases. If the energy level increases, that means it will bring about a higher heat. Heat will be high. Right. You will experience this, that there will be greater amount of heat, isn't it? Because there would be more number of collisions which would happen, higher amount of energy would be produced. Now, then consider the adverse or the opposite scenario. Well, let's suppose I'm trying to accommodate this in a larger area. The air has expanded. So all these molecules, they will now have larger space to get accommodated. So what will happen to the number of collisions happening? Number of collisions will decrease because now the particles are very far away from each other. So energy level will reduce. Energy level reduces. So as the energy level reduces, can we not say that the air cools down? Right. So when we have the condition where the air parcel, its volume gets compressed, right? That is what is also referred to as adiabatic compression, and that leads to heating as a process. When we have an air parcel whose volume expands, that is adiabatic expansion, that also brings about cooling. So that is also known as adiabatic cooling. So adiabatic heating or compression, basically, when we say adiabatic cooling, it is also expansion of air. Expansion of air. So here, the heating and the cooling of the air is carried out purely by the expansion or contraction of air. The heating and cooling is not carried out because there is a heat source or there is a cold source nearby. No. Heating and cooling is carried out entirely by the process of external or by the process of change in volume. So that mode of heating or cooling, where purely by the change in volume you attain the variation in temperature, that is what is known as the adiabatic process. So, for example, so as the air parcel will expand under this lower pressure, or in general, the molecules which are present around, its temperature will fall because of lesser number of collisions which will happen, and hence we experience a decrease in temperature. Whereas when we talk about adiabatic heating, which is also referred to as compression of air, compression of air, that will happen when a cooler, less dense air mass sinks and exhibits an increase in temperature because molecules are forced to a region of higher air density. Due to this, molecules become agitated, start vibrating, indicate an increase in heat. Where do you experience this? Outside in the environment. Where do we experience that the volume will suddenly change? It is understandable when we say that somehow if we change the volume, if we reduce the volume, if we increase the volume, it is understandable that outside in the maybe in lab you might be able to do so. But out in the nature, where is it that the volume change takes place? Let us understand that. For example, suppose you consider a place. This is the ground surface. Here you have the air parcel. Now let's suppose this air parcel rises up. Obviously, because of heating from the ground surface, let's suppose this is rising up. Now, as this is rising up, it is moving into the region where the air density is lower. In the upper portion, the air density is lower. We know that the air density is maximum closest to the ground surface because of the force of gravity. The density of air is maximum closest to the ground surface. So as the air enters into the region of low air density, this is where you will have low air density. So you don't have many molecules in the surrounding. So the parcel of air which is rising up will have some scope to expand. Right. When you move in a crowded bus or a train, you basically crouch over. You basically have all your arms and legs together. You basically move in a compressed state. But suddenly, you move in a metro train where, let's suppose, the entire coach is available and there are a lot of seats. You spread your legs out, you spread your arms out, you take two seats for yourself, and basically you tend to expand. Same is the case with the air. When it encounters the region of a lower air density, it tends to expand. So there is a kind of an expansion of air. And this will lead to the process of cooling, isn't it? Expansion will always lead to process of cooling. That is why as the air rises up, it tends to cool down in the process. So that is where here you observe expansion of air. So during rise of air, hence rise of air leads to cooling. Then after that, let's suppose you consider an air parcel like this, or rather you consider a terrain for that matter, a mountainous terrain. Okay, let's consider this mountainous terrain with a great height, maybe 6 kilometers from the ground surface, which is substantial amount of height. Now, if the wind is blowing in this direction continuously, here continuously the wind is blowing. Now, as the wind is blowing here, the wind will be forced to rise up owing to the shape of the land itself. The wind cannot simply penetrate the mountain and go inside it. The wind will be forced to rise up. So, as the wind is being forced to rise up, can we say it is being forced into an area where the air density is going to be very less? Higher up, the air density is going to be very less. So, naturally, what will happen? The air will expand. As it is rising up, the air will tend to be expansive in nature. It will expand. And as it expands, air cools down. because of the adiabatic process. So here, air temperature lowers. Cold air. Now, this air here, it will come down the slope here. Now, many of the candidates have doubt even in this, that once the air was rising up, why will the air come down the mountainside? Why cannot the air simply, it is rising up, it can keep on rising up, it should escape the earth, it should go to moon, have a jolly good time and then return. Why does it immediately come down? So I hope we are aware that that is not how the air, the force of gravitation generally does not allow for the vertical movement of air. So that is why the air continues to basically stick to the ground surface. Gravitation, basically, it will surprise you how weaker a concept we have about the force of gravity. Many of us, we are unable to fathom what gravity actually is. So just to clarify, the wind simply does not take off like this, that okay, from the mountain next we will meet at moon and then the wind will go to the sun. No. So the gravitational force basically hugs the air. So here also, this will come down the mountain slope. Now, as the air or the wind is coming down the slope of the mountain, can we say it is coming into a region of a high air density? High air density, closer to the sea level, the air density will be very high. Higher up in altitude that you go, the air density reduces. So, as it is coming here in the region of a higher air density, it is going to be forced to compress itself, isn't it? Because it is coming into that crowded area. So, there the air will have to compress itself to accommodate here. Now, here you might have a query. If the air has to accommodate, why will it come there? It should stay where it is, maintain some self dignity and self respect. But the thing is that there is a continuous push which is happening from here also. More winds are coming up, more winds are rising up. Now, all those winds which are coming up and rising up, they will eventually come down the slope also. So, they are pushing them from behind. So, now the air is being forced into the region of a high air density. So as a result, when the air parcel reaches here, what do you experience? You experience a kind of a compression, isn't it? So here there is compression is experienced. As this compression is experienced, it will lead to increase in temperature. That is why wherever you have a rising air column or rising air parcel, wherever you will observe that the air cools down upon reaching a height. And wherever you will have a kind of a sinking air or the air is forced down, you will observe that there is compression which is happening and the air heats up in the process. Okay. Now, after that, we come to the structure of the atmosphere. So when we talk about the atmospheric structure here, atmosphere is not homogeneous. The atmosphere that we have already talked about, that the atmosphere closer to the ground surface, is very different from the atmosphere that you find very high up into the into many kilometers, thousands of kilometers up from the Earth's surface. That atmosphere is very, very different. For example, closest to the ground surface, the air density is very, very high. And closest to the ground surface, the source of heat for the air is the heat from the ground surface. That becomes the source for the heat. But when we talk about very high up, maybe 500,000 kilometers above the ground surface, the molecules are so very far away from each other. You might have few oxygen molecules here, then you might have a couple of nitrogen molecules here, you might have maybe another set of oxygen molecules, so the molecules are so far away from each other, and at greater height, they get hit by the unadulterated, the unfiltered rays of the sun. And the solar rays, they have varying wavelengths, infrared, ultraviolet, X rays. So they have varying different spectrum associated. So when they hit it here, unadulterated rays of the sun, they create that energy. So when you go very high up, it is not as if you will be able to feel that temperature, but each of these particles, they have very high amount of energy. So when combined, the temperature is high. But then that variation in temperature from the ground surface to the higher up, that is not consistent, that is not common, that is dependent on many of the conditions. And each of the layers of the atmosphere have their own different properties of temperature that they exhibit. So let us study about this atmospheric structure, about the various different layers of atmosphere, and let us understand their features. This is relevant both for your prelims as well as for your mains as well. Let me write it down here itself for both prelims as well as for your mains. Now, when we talk about these layers, so the layer closest to the ground surface, that is what is referred to as troposphere. Then you have the stratosphere, then you have the mesosphere, and then you have the thermosphere, eventually vanishing into exosphere, eventually vanishing into the outer space. Majority of the climatic actions and the climatic events that we encounter, all the factors about the lapse rate, etc., that we studied, that holds true for the region of troposphere. Stratosphere is a region where not many climatic events happen. It is comparatively very calm. All the cloud formation, thunderstorm formation, cyclonic events, etc., all of that pans out in the region of troposphere. Further beyond the stratosphere, you have the mesosphere, which is a layer that amongst all the portions of atmosphere, this is the layer which is least understood by us because the planes cannot fly up till that altitude. So we don't have an adequate information gathering system. The satellites fly higher than the mesosphere. So we don't have an adequate information gathering system. So whatever idea we have gained about mesosphere is based upon few of the sounding rockets that we have released, few of the balloons that we have released. Only with that we have some of the idea about mesosphere, but not much of a detail is known. Having said that, up till the top of the mesosphere, still you have slight homogeneous distribution of nitrogen, oxygen, carbon dioxide, etc. Beyond that, you will find beyond the region of mesosphere in the thermosphere and exosphere, you might come across a situation where you have a chunk of gases here and then absolute lack of gases, maybe another chunk of gases to be present here. So you might come across this reality as well. So that is why the layer of atmosphere up till mesosphere, that is also what is referred to as the homosphere. In the sense, you have the homogeneous nature of atmosphere up till that portion. So this portion of atmosphere up till the region of mesosphere, this is what is also known as sometimes homosphere, because of homogeneous distribution of gases. Homogeneous distribution of gases. Whereas this particular portion, this is what is referred to as, beyond that, with no such end limit, this is what is referred to as heterosphere. Heterosphere, because beyond this particular height, all the gases, you don't have the exact control of the gravitational pull also, that all the gases are uniformly attracted by the gravity, are spread out uniformly. So here you have the mixture, or simply presence of random concentration of gases. Okay, so that is what is the distinguishing factor between the regions of the atmosphere also. But when we talk about, let's suppose, troposphere. Troposphere is the region closest to the ground surface, is the layer of atmosphere hugging the ground surface, right? But when we talk about troposphere, this is where you have majority of the mass of atmosphere is restricted into the troposphere. Why? Because all the air particles, the gaseous particles, the dust particles, the water vapor, everything will be highly concentrated in the region of troposphere. That is because of the force of gravity. Now, we all obviously, the air that we live, that we experience, that we breathe, that is the region of troposphere. But troposphere, its height is not consistent across the entirety of the planet. It is not as if it is a uniform sphere around the region of the planet. No, the height varies. The height tends to vary from one season to another and also from one region to another. For example, in the region around equator in the lower latitudes, you'll find that the height of troposphere is close to around 16 or even 18 kilometers in certain instances. Generally, around 15 to 18 kilometers is the height around the lower latitudes. Whereas in the higher latitudes, closer to the poles, the height of troposphere is close to around 8 to 9 kilometers. So there is a variation, a spatial variation as well as a temporal variation, in the sense that even from one region to another there is a variation in height, and even from one season to another there can be a variation in height. So why does that happen? Why is it that there's this variation in height? Because of factors such as, when we talk about, let's suppose, the lower latitudes, we do know that the lower latitudes, they get heated up quite significantly faster, isn't it? And these are the regions of heat surplus, as we have already discussed. So, and the regions of higher latitude, they are a region of heat deficit overall. So what do we have here? We basically have, when you have, let's suppose, the lower latitudes, if I consider this the planet, this is your lower latitude, these are, let's suppose, your higher latitudes. So from the lower latitude, the air, when it gets heated up, it will try to rise up. It will try to rise up, isn't it? There will be a convection current of sorts. A convection current of sorts will be observed here. The convection current will have a sinking column in the region of the colder areas. In the region of warmer areas, the convection current will have a rising column, isn't it? So, because in the warmer areas you have that rising convection current, rising air parcel, hence the height of the troposphere in the lower latitudes is always going to be greater. So, here you have rising air parcel or greater height at equator. Why? At lower latitudes. Because in the lower latitudes, due to heat surplus, there is a rising convection current which pushes the height. Whereas in the regions of the poles, you have the sinking portion of the convection current, which in a way reduces the height. And also the general fundamental of the state of matter that you would have read in class 6 sciences, where if you heat any state of matter, it tends to expand. If you cool down any state of matter, it tends to contract. You would have studied that. Similarly, here also, when you heat it up, it will tend to expand. And in the lower latitude, it gets heated, so it will expand. In the higher latitude, it gets cooled down, the air is cooled down, so it will tend to contract. So lower latitudes, due to heat experience an expansion in the column of air and in poles or in polar areas compression due to cold conditions. Right? So that is what leads to varying height in the region of the lower latitudes as well as in the region of higher latitudes. This particular concept of troposphere and how heat is transmitted in the troposphere will be helpful to us as we move ahead with the next modules also. This is where we'll restrict the session here for today. Tomorrow we'll carry this discussion forward, and yes, polar areas means higher latitudes. Tomorrow we'll carry this discussion forward. We will move ahead with the other portions of atmosphere and temperature as well. Okay. So in the meanwhile, I'll take a few questions. Uh, I have worked definitely take almost more than 10 revision, and each understandable word is translated for understanding. And then seeing my answer evaluation marks, it made me so sad. You should not be. You should not, absolutely not be worried. Think about it like uh, as of now, the only thing which should make you sad is what happened last night in the World Cup. Other than that, I don't think there's any reason for anybody to get sad. You are in that stage of preparation as of now where you should be able to analyze that what are the areas that have been pointed out. Don't take it on as an ego battle that I have worked so hard, I have scored less marks. What this mentality or mindset will lead to is that next time when you work hard, you will be afraid to write answers, in the sense that you will be afraid of failures. That I have worked so hard, what benefit of it will be if I again get less marks? So you will lose trust with the entire system itself and you will stop giving the exams. Don't worry about it. As of now, your effort should be that how do I find individuals in my life who are able to point out my mistakes. The greater number of pointing out of the mistakes that happen at this stage, better it will be for your improvement of your answer paper also. Okay. And Anjali, in Baiju's book, the average height of troposphere is given 16 kilometer and 6 kilometer above poles. What have I said? 8 kilometers. I have said 8 kilometers above poles. Fair enough. It is, see, understand, it is not as if 16 kilometer is that kind of a thing where if you go to 16.1 kilometer or 17 kilometer, it will be completely different. No. In certain seasons it can go to 18 kilometer also. In certain season it can come to 15 kilometer also. In the region of the poles it can go to 9 kilometers also. It can come to, it is just that in from our childhood days we have drawn that kind of a diagram that okay, the earth is a circle, around it the crust is also a circle, inside it the mantle is also a circle, and outside it the atmosphere is also a circle. That is why we always think in a symmetrical, that is it 16, is it 17, will they cut my marks if I write 16? First of all, UPSC will not be asking this question that at what height does the troposphere end, because UPSC also knows how ambiguous that question is. Any person, any individual who knows a slight bit about climate will tell you that the troposphere, stratosphere, mesosphere, it is not as if their height is fixed. Their height keeps on varying over a period of time. Okay. But sir, you tell temperature increase with change in height called positive lapse rate. No, that is called negative lapse rate. In case I have told that, please correct it. Whenever the temperature increases with the increase in altitude, that is called as negative lapse rate. Positive lapse rate is when temperature reduces with the increase in altitude. Does this reduction in height of the troposphere depend on Ferrel and Halley's cycle and wind pattern? See, another intelligent individual I have. So, does the reduction in height of troposphere depend on the Ferrel and the Hadley's? It is not Halley's cycle and wind pattern. It is Hadley's cycle and wind pattern. So, it does impact the Hadley cell also. It does impact the Ferrel cell also. It does impact the polar cell also. So, it is also impacted by the rising and the falling of the air there. But overall, you can summarize it by saying that rising air in the lower latitudes, you have because you are aware of Ferrel cell, you would be aware that around 60 degrees also you have a rising air column. But that does not mean that around 60 degrees suddenly the height of troposphere is lifted, does it? So varying factors are involved. So on an average, I have taken, or the generalistic view I have painted forward for you, that the rising air column in general will lead to an uptick in the tropospheric height, and a sinking air column will bring it down. Okay. Uh, Himani, does this high reduction in, okay, that I have answered. Shyam, why air goes up when there is any obstacle? Why not a side path? Okay. Shyam, let me paint a picture for you. This is where I always maintain the better you are at imagining things, better you will be at in geography also. Let's suppose you consider India. Now, in India, from the region of Jammu Kashmir all the way till the region of Arunachal Pradesh, you have the Himalayas. If the air is coming here, are you saying or are you advocating that the air should then start traveling like this? They should come to Uttarakhand, take a break, move to Himachal Pradesh, take a break, move to Jammu Kashmir, then eventually reach the region around Karakoram, and then eventually come down because they have to reach here. Then why will they reach here? Why will the air want to reach here so bad that they will cover these large distances around the mountain? Is it a fairy tale going on that I have to go to that house? Is it a kind of a Cinderella story that I have to go to that house, so that is why I will traverse those mountains? No. Air does not know direction. Air does not know what is north, what is south, what is east, what is west. Air travels by a different mechanism. An obstruction comes in a pathway, the air will move above it if possible. If the obstruction is very high, that it can't rise up above it, then there will be a different mechanism altogether, which we will deal with it. But then, when the air comes across this mountainous area, and when you think about a mountain, I what I have gathered after covering the portion of geomorphology along with all of us, when we think about a mountain, please don't think about that this is an isolated structure in between nowhere. Mountains are your continuous structure in general, right? You will have great heights associated continuously. For many hundreds of kilometers, you will have that height. So where will the air go? Air will have to go up. Okay. And Biswajit, why this air gets compressed when it comes down from the mountain? Why won't it get compressed? That is what the explanation I was giving when you were asking a question about, is it directly proportional to the density of air, if I recall correctly. So basically, if you have a mountainous area here, if the air is being forced down into this region, this is a region of high air density. High air density. So if the air has to accommodate itself here, won't we say that the air will be accommodated? Or if the air has to come into that area, won't we say that the air has to get compressed? Because that is the region of a high air density. This is the region of low air density, where the air density is very low. Here the density will be very high. So if the air is being pushed into the area where already a lot of air particles are present, so for the newer particles to come in, they will have to compress, they will have to adjust themselves. That is what brings about adiabatic heating. Asta, how to remember plates with all the three types of boundaries? Just revision, my dear friend. Asta, please don't try to learn these plates. The moment you try to learn these plates, you will commit mistakes. What you can do is, when you create these answers, or when you talk about the convergence or different types of convergences, divergence, try to seek for examples. When you look at the examples of convergence, continental, oceanic, etc., that is when you will encounter many of the smaller plates also, larger plates also. And your aim should be that for each of these examples, I should, or for each of these instances, I should have 3 to 4 examples in my mind. That should be more than sufficient. Okay. Dinesh, you can send the uh, answers at IES Live. The evaluations, etc., will be done. Okay. And positive lapse rate, Uni, is when the temperature reduces with the increase in height. Negative lapse rate is when the temperature increases with the increase in height. Positive lapse rate, we have seen the reason why the temperature reduces with the increase in height. Negative lapse rate, will come across it that there are certain climatic conditions, or there are certain conditions where you experience that higher you go, warmer it is. So we'll come to it. Okay. At several heights, the air gets cooled due to temperature. Yes. Praveen, what I said about the Tonga, it is not Donga plate, it is Tonga plate. Tonga with a T, not a D. So Tonga is basically a set of islands that you have in South Pacific. So there, because of convergence of the Australian and the Pacific plate, you have the division, or a much smaller Tonga plate, which has also been in existence. Now, if you have the Australian plate, let's suppose like this, the here you have the Tonga plate, think about it, and here let's suppose you have the Pacific plate on the other side. So this is your Pacific, this is your Tonga plate, and this is your Indo-Australian. So here there is convergence which is happening here, but here divergence is happening on this side, right? It is here that the Tonga plate in itself, along with the Indo-Australian plate, there you experience divergence. Example of negative lapse rate is only the case of stratosphere. Stratosphere has the example of a negative lapse rate. Negative lapse rate is also observed in the conditions of temperature inversion. All the different types of temperature inversion, you experience negative lapse rate. Positive lapse rate is what you experience in troposphere. That is the positive lapse rate. Does that mean temperature is proportional to density? No, not at all. Please don't have, because in stratosphere, comparatively the density is lesser than the troposphere, but stratosphere has a higher temperature. So please don't come at these conclusions. Sujal, it is good to know that you're finding interest in the subject. Why geography kept in arts despite of the science? Because it is the eventually all this portion that you are studying, you are studying for the basic reason, in order to understand the human pattern for settlement, for economic activities, for their own behavior also. So the different types of ecology surrounding, so that is where it has got the arts connotation. That is why it is kept in that arts portion. All this portion that we have studied, I understand it appears to be scientific, but this understanding helps you understand what kind of migration patterns are indicated by individuals, what kind of behavior is indicated by certain areas, what occupation is observed in certain areas, what are the settlement patterns, what are the location of the industries. All of that is based upon these findings. That is why. Can cliff-like structure be created due to sinking down of a riverbank, or a structure like that can be created, what can be referred to as a canyon? Okay. Region along water bodies experience warm winds during the night. Is that advection? Yes. Dunesh, correct. Shazia, if the earth is spherical in shape, so is this possible to cross all layers of earth and we reach another side? If you can, yes, obviously. What is the process of ozone layer depletion? Sanjana, we will study that under portion of environment ecology. Why up to mesosphere it is referred to as a homosphere? Because of homogeneous concentration of the gases. Beyond that, you have gases which are not present in unified concentration, they are spread randomly. Okay. And Ziba, is heat level always constant in adiabatic process? Most of the times. But then also, Ziba, you have to understand that for an air parcel, the concentration of water vapor and the concentration of other gases, etc., that can vary. So that is also what creates that variation. Okay. See, the thing is, I understand that when we approach it in a scientific manner, it can become slight problematic for many of us, because from our childhood days we are used to that condition where the teacher would come, give us the notes, tell us that this is where the questions will be asked from, so rectify and mug up these notes. I'm sure many amongst you would have studied social sciences just like that. But when it comes to UPSC, that is where the application of this is involved. So if you are covering, and I always believe this fact, if you are spending all this energy, all these resources into studying a subject like geography, where maybe you are not trying to become a geographer in the future, and I'm sure you are not trying to become geographer in the future, but if you are studying this much, this subject, there's no reason why you should not be aware of the deepest of the details here. Because if you are spending energy and resources, dig your teeth deeper into the concept. Once you understand the concept, you will not be required to revise this. So that is why I am getting into the scientific process of it, because this is about understanding rather than learning. Okay, I don't want you to learn in portion in that subject. Okay. So, fair enough. That is where we'll end the session here today. We will initiate the discussion from here itself tomorrow as well. Till that point of time, do take care of yourself. Do try to revise. And those of you who had not appeared for the weekly test, try to appear for the objective test at least. It is not a matter of how much you score in that objective test. It is a matter of, even if you score zero in that objective test, I don't care, as long as you take some learnings from it. That why am I committing mistake, where am I committing mistake? So do take up those tests, try to write answers also, and that's all. Relax. See you tomorrow. Goodbye. Thank you.